You out. So I will not waste any time. I will just say hello from Oslo, and then we'll start with the first presentation of the day. The team this morning is homogenization, and I will introduce a veteran in this business, Peter Domonkos, and you will talk about a new version of AQUA. So please, Peter.
Good morning, everybody. So it is the time to present AQUA version 5. It is the first time to present it. First, I would like to express my thanks to for the support to the Catalan Meteorological Service. And does not work. I cannot move the slide for some reason. Something is not good. It's frozen. Cannot move this.
Peter, you can try to stop sharing your screen and try it once more. Otherwise, if you prefer.
Does not work. Yes. Yes. Un momento. Ay. It is unrated, and now I don't know what to do. I cannot move. No, something happened.
Now it's moving.
Yes,
Yeah.
but now, but it moves, but not in the way that I wanted, and I cannot go back.
Okay.
You want me to try to do the screen share for you?
I don't know what. It did something what I usar función de compartir.
Peter?
I suggest to change my presentation with somebody else, and I try to try some options with my computer, because it is an unweighted technical problem that I cannot move the slides in the order and the time when I would like it. Or another option that I sent you my presentation, and I ask an assistant that somebody
Peter,
moves my presentation.
I can do this for you. Can you hear me?
Yes, but at this moment, I cannot even go out from my presentation.
I fixed that.
Okay.
So I'll do the sharing for you, and you'll tell me every time you want me to change your slide. Okay?
Yes, it is a solution. Sorry.
Okay.
So we start to this with the AQUA version 5. The supporter is the Catalan Meteorological Service. Next slide, please. We turn back a bit to the multitask project results. I here recall that we have a paper published in the Journal of Climate at the beginning of this year. Was published. It is a part of the multitask project results, not all the results of the multitask, but really a large number of test data sets were used. And from this table, you can see that in most cases, AQUA In this case, AQUA version 4, obviously it was the previous version of AQUA. In most cases, AQUA produced the best results. All the green cells indicate that the AQUA was significantly better than the other methods. The acronyms for the rows are test data sets. There were used here 12 test data sets. All these test data sets were monthly temperature test data sets for mid-latitude European temperature climate. It is a relative, maybe it is a limit somehow the representativeness of these tests, but the variation of inhomogeneity properties was very wide and sophisticated. For the columns are for the efficiency measures, and there were one case, it is shown with red, when another method than AQUA was significantly better, gave significantly higher accuracy. It was the pairwise homogenization algorithm by Matthew Menne, which was developed for the first to the homogenization of the United States temperature network. And it is interesting because it was a point for the development of the newer version of AQUA. So this weakness was an indication. Next slide, please. And now about AQUA version 5, 4 kinds of novelties. In the statistical method, break detection with combined time series comparison in the first homogenization cycle. It is directly for reaching improvement in the treatment of the synchronous breaks. The pairwise homogenization algorithm is better in certain cases when the time series have synchronous or semi-synchronous breaks. The other thing is the widened user options in the initiation of the homogenization procedure. An absolutely new option is the metadata use, and AQUA version 5 has also interactive mode optionally. Next slide, please. Now about the combined time series comparison. So the simplest idea would be that if the pairwise homogenization algorithm, which is a homogenization method, not a time comparison method, the pairwise homogenization algorithm, following its experience, simply change the use of composite reference series to pairwise homogenization, or pairwise comparison. But pairwise comparison has also drawbacks. In pairwise comparison, the signal-to-noise ratio is lower. So what is offered in the combined time series comparison, what is solved by the combined time series comparison, is unifying the positive features of the pairwise comparison and composite reference series use. In the combined time series comparison, in its first phase, a pairwise comparison is performed, and the detected breaks of this phase are prescribed as obligatory break positions in the second phase of the homogenization of the break detection of the same homogenization cycle. Next slide, please. Yes, the pieces of pairwise comparison results are evaluated, and this evaluation is adopted from the Menne method, from the United States method. But there is one difference in the application in AQUA, because in AQUA we use always optimal step function fitting and cosinus-Liazri criterion. And when the test statistics of the cosinus-Liazri criterion give similar values, the AQUA version 5 considers the similar solutions with weights. The total weight is always 1, but in this way, the number of neighbor series which contributes, which indicates a break for a given station and a given year can be a fraction, not a whole number, because weights are applied. I wanted to give here an illustration in the last day, but now I cannot show it because it is a conserve. But we show now. No, further details about the combined time series comparison you can find in the special issue of the atmosphere application of homogenization method for climate records. I am the guest editor of this special issue, and it still accept submissions until the January of next year. I still wait for the submission. It is a quite good impact factor, open access, and yes, it has price, but if you send email directly to me, a discount is negotiable. So yes, next slide, please. I mentioned that AQUA version 5 has widened initiation options. Here with blue color is shown which are these options. Originally, the threshold special correlation is 0.4, but now in the new version, the user can change it. A new option is the metadata use. If you define an appropriate way, a metadata table, the program will use it automatically, but if you don't use, the program will run without metadata use. And another option is that you can define the set of the time series for which you expect homogenized results. Why it can be useful? Because AQUA for large size input data sets, for simplicity now, I say that for larger than 40 time series, but it depends on also the correlation relations between time series. The AQUA automatically divide the large input data sets to networks. In these networks, although again, each time series are homogenized together, the network homogenization produce output only for one candidate series for which the network structure is optimized. Therefore, on the one side, it is recommended to use as many time series as you can, even short time series, even fragmented time series for the homogenization. But likely, you in a large size input data sets, you expect results only for the relatively high, relatively large size, the relatively complete time series, and you can spare time with defining the set of requested time series. Next slide, please. Metadata use. As I mentioned, the pairwise comparison may result in fraction, considering the numbers, how many neighbor series indicate that a break is present for a station and a year. Metadata acts as if one more neighbor series would confirm the presence of a break. It gives an extra 1.0 weight to a given station and a given date. And beyond this, in the final stage of the homogenization procedure, in the refinement of the break dates, metadata also taken into consideration. Next slide, please. And AQUA version 5 has also interactive mode. The interactive mode, again, more useful for the large size data sets when multi-network homogenization is performed. In the interactive mode, user may edit the network. The network first are constructed automatically by the AQUA version 5 procedure, but the user can edit this network. The user can define special correlation thresholds for any network of the data sets. And another option is that the user may edit the break list after the first homogenization cycle Yes, it can be applied both for one network homogenization and for multi-network homogenization. This third option does not depend on the size of the data set. In the addition of this break list, the user can use the information about the automatically detected breaks and outliers, about the scores of the score table of the pairwise detection results, and also an Excel table is constructed by the procedure, and from this Excel table, the user easily can make figures to study the most important time series, how they are relation. These are annual anomalies, and these annual anomalies can be examined by the user. Unfortunately, I would not be able to show examples because in this Conser version, I have not provided it. Next slide, please. Of course, in bivariate homogenization, two break lists are present, and two Excel tables are provided for the user to examine which details are the break list should be corrected, if any. Now, I don't explain more about bivariate homogenization because I did it in earlier presentations. In multi-network homogenization, it is another option. In multi-network homogenization, users may opt to repeat the last network homogenization. So, for instance, you have 500 networks. You does not need to wait until the end of the homogenization procedure. If you see an error, a suspicious thing in the homogenization of the last network, you can repeat the homogenization of this network with a re-edited network structure or with treating another way, the break list, etc. Next slide, please. Yes, about the accessibility of AQUA. The AQUA version 5 can be purchased. It is not a free software. Now the AQUA version 5 can be used by me or by the Catalan Meteorological Service. Further information about AQUA version 5 is provided in the web page. The manual is deposited to another place because its size. The manual is freely can be read. This is the manual of AQUA version 5 about the combined time series comparison. I mentioned the article in the atmosphere in the special review. In the special issue of the atmosphere. And the AQUA version 4 remains a free software together with its manual, and the full scientific description is available from here. Next slide, please. Finally, I would like to speak a bit about unresolved problems. So, for instance, we have a lot of quite good efficiency tests with monthly temperature test data sets, but it is not enough. We should need more about with test data sets of tropical regions, with sophisticatedly developed test data sets for other climate variables. So a lot of things, and also other items listed here are unresolved now. With which I think to contribute. Yeah, the first is the AQUA version 5. The second is that now I write a book, and I hope it will be published before the next data management workshop, because I hope that it will be ready and in the second half of the next year. After then, we must wait for its publication. I have a contract with the Elsevier. The Elsevier asked me to select a rather wide topic. So the topic will be rather wide, observation, data quality control, and homogenization. And I hope that I will serve the community with this book. My idea with the special issue in the atmosphere was also that I think that a good collection of a topic can serve well the development of the scientific area, and it is useful for the scientific community. So it was my initiation. I don't know how well I captured the intention of the community, but these are my intentions. So all these positive intentions from my part, and I thank you for your attention. Conclusions are not. The conclusion is that we must work further. Thank you.
Thank you, Peter. I think that's the standard conclusion. We still have work to do. So I think we have time for one quick question to Peter, if there is anyone. So please raise your hand and we'll. I don't see any hands. So to keep up with the time schedule, I think we proceed. So the next speaker will be Bertrand Cedric from the Belgian Met Service, and you will talk about the homogenization of Belgian historical precipitation time series. So please, Cedric, go ahead.
Hello, good morning, everybody. Precipitation is one of the essential climate variables identified in the global climate observing system. High-quality long-term precipitation series essential information for, among other things, to identify and understand climate variability and change, for identifying emerging trends, for supporting the development of sustainable water resources and flood management system. In Belgium, precipitation data have been recorded since at least 1880 in different parts of the country. The Belgian Climatological Observation Network currently counts 207 pluviometric stations, but the number of climatologic stations maintaining daily precipitation HAMMON's records vary over the time, as illustrated in the figure here. So each HAMMON of climate data have been recorded since the early stage of the climatological network, wherever the existing data heritage was largely underexploited because historical information still remain in hard copy and fragile media. I mean, data unwritten kept in the original daily weather report, and until recently, daily precipitation HAMMONs from the Belgian Climatological Network were only available in a digital form for a period starting in 1951. And only 12 long-term precipitation time series were made available in the first digitalization stage many years ago. So fortunately, ERMI has undertaken a strong effort of digitalization over the past years, and daily precipitation HAMMON from 623 pluviometric stations have been digitalized for the period 1880 to 1950. But because only a few long time series were identified in the central database after the digitalization process, it was necessary to construct additional long-term series by merging climate records from neighboring stations, provided that strict conditions were satisfied in terms of distance, elevation, and the number of sub-series. At the end of this process, continuous time series of daily data have been identified for 19 centennial series starting before 1912, including 9 covering the full time period 1990 to 2000, no, 1880 to 2019, and 110 series for the period 1951 to 2019, hereafter referred to as long series. So the figures show the series location within the Belgium territory. 3 centennial series and 52 long series are derived from a single station data. The majority of the centennial series, 6 series, are built from precipitation data of 3 different stations. 1 centennial series includes a maximum number of 6 different station data, and 2 long series include up to 4 different station data. It is worth noting that because of station closure in the recent year, only 8 of the 12 previously derived historical precipitation time series could be extended until present. So as extensively discussed in the literature, use of raw instrumental data pose a number of specific problems. Firstly, any observations are likely to contain erroneous values. So validation of this observation is just essential in order to detect and correct where possible these errors. And secondly, measurement conditions generally change over time, and this may introduce artificial break in the data that do not reflect the variation of the climate. So as an example, in illustration, the slide presents the different model of manual rain gauge that have been in use for a time in the network. And in case of precipitation, progressive improvement of instrumentation can generally introduce an artificial systematic increase. I mean, in case of manual rain gauge, because the shift to manual to automatic is generally followed by a decrease. So the homogenization of the observation series is therefore essential in order to eliminate non-climatic influence from this series. A 2-step quality control was applied to daily precipitation record. Firstly, the digitalized data was checked on a semi-automated basis against typical carrying errors, unit conversion, and 1-day time lag. And secondly, fully automatic QC procedures were applied to all the daily data to ensure physical limit consistency and spatial coherence of the data. So the method opted for homogenization of the monthly precipitation time series in Belgium relied on the use of the HOMER software. The monthly homogenization was carried out separately for the centennial series and the long series. 23 additional foreign series were considered to help the homogenization of the Belgium series, and 6 of them, having data since 1880, were also used in the homogenization of the centennial series. The long series were divided in 12 clusters for the homogenization, and the centennial series into 2 clusters respectively. So at the end of the treatment, the quality of the homogenized series was evaluated according to several criteria. The minimum detected magnitude associated with each series, which is the standard deviation of the different series between the tested series and each neighboring series, the number and longitude of the break, and the cumulative correction of the series. So while varying from one series to another one, the HOMER breakdown magnitude is in the order of 7% for the centennial series and 6% for the long series. It is typically 5 to 8% in case of well-correlated precipitation series. So 5 centennial series were found to be homogeneous, but 32 breaks were detected by HOMER across the other 14 centennial series. Multi-break were found in 9 series. And regarding the long series, the majority of them do not present any break, and 35 series have a single breakpoint. And multi-break were detected by Homer across the 10 others series. So the figure presents the frequency distribution breakpoint magnitude for both centennial series and long precipitation time series. And across all series and detected break, the mean absolute amplitude for the centennial series was 16% and 13% for long series respectively. The largest detected break has a magnitude of plus 35%, and it was found in 1928 in a previously derived historical series that contained daily record from a station operated by the Belgium Roads and Bridge Administration at starting sub-series. And for a time, station of this administration used a rain gauge much larger than those of RMI, which was placed on a woody support at an height of 2 to 2.5 meters above the ground. And because the amplitude of the detected break in this series is larger than our threshold of 30% change, the series has been discarded. On the other hand, the largest detected reduction, namely minus 27%, results from the combination of two elements, station relocation and automation at the end of the 90s. It is worth noting that this decrease is nearly compensated a few years later by an increase of 25% when a new type of automated rain gauge was installed. So precipitation trends before and after homogenization of the centennial series are evaluated by the slope of a linear fit. The estimated trend are provided in the table together with the p-value associated to the slope of the linear fit, and a significant level of 0.05 is considered to determine whether the trends are statistically significant or not. So in the table, these linear trends are given individually for each of the 9 longest precipitation time series, for the mean of the 9 of this 9 series, as well as for the mean of the 18 centennial series, respectively. So while the trends are positive in both the original and homogenized series, the impact of the homogenization differs from one series to another one. As an example, the trend is reduced after homogenization in 4 series, illustrated with the minus blue, while increased in 5 of them. And the largest trend reduction as well as increase after homogenization are both due to a station relocation. And when considering all the 9 series together, the mean precipitation trend after homogenization is in the order of 17% per decade and about 1.21% per decade on average for the 18 centennial series. Regarding the long series, an histogram of the trend before and after homogenization is displayed in the figure. A reduction of the range of the trend as a result of the homogenization is clearly apparent. So now the figures show the average evolution of precipitation in Belgium obtained by combining the measurement data from the 9 centennial series starting in 1880. On the figure, the average annual total are represented by the deviation in percent to the average of the reference period 1961 to 1990. So if we compare the average of the last 30 years with that of the first 30 years of the period, we see an average increase in precipitation of about 15.4%. or 16.40% when considering all the 18 Sentinel series. And this change is mainly due to the particularly dry character of the period 1880 to 1909. Conversely, the 1890s and the years 2000 show a majority of wet years, and the years 2010 are mostly dry. However, the representation of average rainfall in Belgium can mask important regional differences. So in order to use the maximum number of available series, the spatial analysis of annual and seasonal trends cover the period 1951 to 2019, for which we have 110 homogenized series. So on average, over all the series, normalized precipitation increased by plus 1.1% per decade, but this increase is generally not statistically significant. Indeed, as shown in the figure, the increase in annual precipitation over the considered time period is statistically significant only for 4 regions of the polder, sandy Flanders, sandy still Flanders, and the Gaume, as indicated by the black dots in the figure. Now let's have a look on the seasonal trend. The figure presents the observed change in the normalized seasonal precipitation in percent per decade based on linear trend for winter, spring, summer, and autumn. And the color bar is the same for the 4 seasons in range for -4 to plus 10% per decade. In the 4 regions where annual precipitation have increased significantly, there is also an increase in seasonal precipitation, but it is only in winter that the increase are significant. However, this is not the case in the other part of the country. For example, the most pronounced non-significant decrease in normalized precipitation is observed in the Haute-Fagne during the summer period. So on average, over the series as a whole, the most marked change in precipitation pattern occur in winter, with an average increase of plus 3.5% per decade compared to plus 0.7% in spring, plus 0.2% in summer, and plus 1.1% in autumn. But all these average trends are not statistically significant. So to conclude, a new data sets of quality control and homogenized monthly precipitation have been created for Belgium. It is expected to be updated on a regular basis. The new dataset indicates an average precipitation increase of about 1.2% per decade from 1880 and of about 1.1% per decade from 1951. However, the computed precipitation trend in long series are generally not statistically significant. Another point is the fact that the pluviometric network operated by RMI is still largely manual, with less than 15% of the rain gauge automated, and because a number of our voluntary observers are becoming elderly, we have been faced with an accelerated rate of station closure over the past few years, which is unfortunately not compensated by the opening of new stations. And as a result, 39 long series and 5 Sentinel series have been lost over the past 5 years, as there were no nearby station fitting or bridging and appending criteria. And finally, we hope that the current digitalization of precipitation data from the station initially operated by the Belgian Road and Bridge Administration during the time period 1880 to 1950 will offer, when completed, an opportunity of developing new Sentinel series. I thank you for your attention.
Thank you, Cedric, for your presentation. Are there any questions? Yeah, there's one from Kairi in Estonia. Should I read it, or will you read it yourself? As I understand, you found breaks after automatization in Estonia. We have automatization more or less same year in 2003 in all series, and due to this, Homer can't recognize it. How is it possible that you found automatization influence and breaks?
Sorry?
She asks whether in Estonia they have a problem that all the stations were automated the same year. Okay. Then it's very difficult to detect the breaks because there you have the more or less the same response in all stations. But how is it in Belgium? Did you have
it's totally different because only, as I say, 15% of our stations are automated, and the shift from one instrument to another one is not done at the same time over the full network. It's done progressively, so we still have. It's still possible to find a reference series to perform the homogenization.
Thank you. Are there other questions? Please raise your hand. Yeah, Erik Engström from SMHI, please.
Yes, yes. Thank you for the nice presentation. I wonder, you showed in the beginning of your presentation, I think that you had 3 different rain gauge types during the whole period in this study. Have you done any, comparison of the different rain gauges and made correction before the homogenization, or did you count on the Homer homogenization to adjust for the different types of rain gauge?
Okay, no correction was applied on the value before the homogenization. We have used the correction coefficient provided by Homer. Yeah, only for the equal time series we have applied for which we have long parallel measurement. We were able to perform our own to calculate our own correction coefficient when moving from one instrument to another one. But for the climatological network, we fully relied on the correction provided by Homer.
Thank you, Cedric. And I think if there are no further questions, I can't see, then I think we proceed to the next presentation. So thank you again. And the next presentation will be given by Maurice Buchmann from the Snow and Avalanche Research Institute in Davos. And it's about homogenization of snow. So please go ahead.
Thank you. And yeah, I just start. The title here is Homogeneity Assessment of Swiss Snow Series. I think the title in the abstract was a little bit different. It says something about evaluation of break detection methods for Swiss Snow Series, but it's mainly the same. So quickly skip that one. And for the motivation of why we're doing that is, of course, because inhomogeneities are omnipresent in meteorological time series. And the main causes normally are instrument changes, which is quite important that it does not apply to snow series. And I can come back to that in a second. Then we got other reasons are observer change or station relocations, change of station environment, and obviously a possible combination of the above. And again, inhomogeneities are extensively studied in various fields, so we got plenty of established methods to choose from. However, or maybe it's a little bit surprising that there are only very few studies covering homogenization in alpine snow. So that's another reason why we look into that. And these are a couple of questions we basically want to have the the answers to is how well do semi-automatic break detection methods agree when applied to snow series, and which methods or setups work or are best suited in terms of ease, user-friendliness, or efficiency, and is the performance of these methods, is that dependent on any station characteristics as altitude or climatological snow cover class, we call it here, or that could basically be the climatological mean snow depth or maximum snow depth or something like that. And of course, how many, or if possible, even which types of breakpoints can be explained by metadata. And to come back to the point I made before, that the change of instrument is not important for snow or snow measurements, because we are dealing with manual snow observations. And the manual snow observations, they are basically the same for, I guess, for about, I don't know, for quite a long time. So it's, and they actually performed every day between November and April. So there's a snow field or a measurement field, and snow depth is just read off from a metal stake. And the height of new snow, there's a so-called snow board, which is placed parallel to the old snow surface, and then if there is snowfall during the night, then on the following morning the observer measures the snow that has accumulated on that snowboard. So and it's actually quite important, because there are no automatic measurements that can actually deal with measuring new snow quite accurately. It is possible to measure snow depth with automatic methods, but not new snow. And this is the data we used. We used the monthly mean snow depth derived from manual observations. We considered data between 1961 and 2020, and mainly because during that period we got the highest amount of reference series. We selected a station so that they had no missing values, but obviously they have various lengths, but the minimum length is 20 years. That results in 150 stations for Switzerland. And maybe one or two sentences about metadata. Metadata is in general available, but it's for snow, it's mainly on annual resolution, and it only covers relocations or observer changes. But it's quite important to stress that it's not complete, and it could be a bit inaccurate. So there could be a mention of relocation that happened a couple of years before, or observer change. You could just mention yes, observer change yes, sometime during the last couple of years or something. Then for the break detection methods, we used three. We used AQUA, Klimator, and Homer. And AQUA, that was version 4. And our procedures are basically, we just ran these three methods with various settings. We compiled the metadata, and in the end, we defined the valid breakpoint as a breakpoint if it was detected by 2 of the 3 methods above, within a tolerance of plus minus 2 years. And that tolerance is basically because we wanted to check it with available metadata, and because the metadata is a little bit uncertain, so we wanted to make sure that we cover more or less the same break. And then we aggregate and compare the data. Here the different setups. For AQUA, we just use the precipitation mode, and all the other settings are set to default. We retrieve the breaks from the automatically generated file. Climator, we set standardization to 2, rest to default, and again retrieve the breaks from file. With HOMER, we played a bit around with the available settings. So we choose ratio mode and pairwise detection. Here we set the minimum correlation to 0.9 and the minimum reference series to 5. Detection was based on annual values, and because HOMER, we used it in the manual detection mode. So here again, break is defined if it could be found in 3 out of 5 reference series. And these are the preliminary results. It's quite important to stress that these are not the final results. First, it's just an overview of how many breakpoints are detected by each method. Just if we just sum up the detected breaks, we can see that AQUA detected about 211 breakpoints in 150 series, Climator about 157, HOMER I think is 41, and if we just look at the metadata and take and treat every mention of relocation or observer change as a potential break, we would have well over 350. So obviously that is not particularly good, or something you can work with. And so here we put that in, that a breakpoint is only a valid breakpoint if it is detected by 2 out of 3 of these methods. And here is the comparison. He's just shown the metadata just to compare that, because I've got a huge number. And yeah, if you look at just purely from the metadata, we would have 10 homogeneous series and 140 which are inhomogeneous or that have at least one breakpoint. And if you apply the definition of the breakpoints from above with the 3 methods, we would have 122 homogeneous series out of 150 and 28 series with at least one break. And just to compare that to one of the studies that exists, Schönheit al. They reported 71 out of 96 analyzed Swiss series were to be homogeneous. They just used the method Prodige, but yeah, just one method. So that's just to compare our values a little bit too. Then obviously, if you define a break, sort of a composite break, it has to be identified by at least 2 methods. We can look at, we can have a look at how this pans out here. And here on the right side is the number of breakpoints that we get if we have the combination of AQUA and Climator is the red one, AQUA and HOMER, and Climator HOMER down here, and the green one, or the green area here, that is actually here breaks are detected by all 3 series. And we see that the combination of AQUA and Climator produces the largest shares. It's about 17 stations, and AQUA and HOMER, in this combination, we get 10 series. And Climator HOMER, there's only 1 series down here, and that one is also sort of confirmed, and confirmed is probably a bit of a wrong word, because confirmation by metadata, in the sense that it's written in the slides, it's basically just that it is mentioned, something in the metadata is mentioned at the same time that we found a breakpoint. next slide, it gives a better overview. So in total, we detected 33 breaks in 28 series. That is, we got 23 series with 1 break and 5 series with 2 breaks, and no series with more than 2 breaks. And about 50% of these proposed breaks can be explained, or some sort of indication can be found in the metadata. And again, here it's basically the same as on the other slide, and a bit more graphically available. And a very quick preliminary summary would be that if we just use AQUA and Climator, we can identify 22 breakpoints out of 33. And if we just were to use Climator and Homer, we would only identify 1 breakpoint. That leads to, at least to the idea that a combination of various methods is probably a good way to look at it. And yeah, as I mentioned before, 50% of the breakpoints can be found, or something can be found in the metadata. Obviously, there are quite a lot of open issues here. The main things we want to find out are why do these methods perform in the way they perform? So why can we only find 1 break with the combination of Climator and Homer, and 17 with AQUA and Climator? Could it be that the performances are somewhat dependent on the climatological characteristics of our stations, or dependent on sea level or the climatological mean snow depth? That is still ongoing. And obviously we didn't answer the question which method we want to use in view of our homogenization efforts for Swiss snow series. And the other quite interesting part is also, if we have about, for 50% of the breakpoints, we have something in the metadata, and we want to see if there's a certain type of breaks that can be detected. So our hypothesis is that observer changes is probably not related to breakpoints, that it's more relocations of stations, but again, that depends a bit on the available metadata. But that is still ongoing as well. And yeah, that's it. That's my presentation. Just maybe 30 seconds here. You can see the same measurement field as on the other picture before, but here you got the automatic measurement station as well. So here the automatic snow depth measurement would be around here, and basically the main problem with that is it just measures on one particular spot, whereas if it's a manual observation, the observer walks into the field and it can sort of determine if it's okay to say we got 1 or 2 centimeters of snow here, or if it's basically snow free. So yeah, that's it.
Thank you, Marit. And you put it on. Questions? Are there any? Please raise your hand or put it in your question in the chat. I have one while waiting for the next one, and it's actually relates to the last picture, because there are some stations that are on the limit where you have a stable snow cover or not, and probably they are also changing due to the warmer climate. Do that kind of pollute your analysis, and what you do with those stations that are not that?
No, it's a absolutely fair question, and for this analysis here, we just pulled all the available stations we had. So we have stations in the mainland of Switzerland that are on 400 meters above sea level that hardly get any snow. We got stations in the southern part of Switzerland which got snow, well, but yeah, which you wouldn't say they have a continuous snow cover. But yeah, that's actually one of the points we wanted to check if these methods are, or if there are significant differences, or if these lower stations, if you can actually do something or can actually detect any breaks, because well, it could well be that because there is not enough data, so there's probably no point in detecting anything, or so. But that is still ongoing to shortly answer your question.
And are the trends different in different parts of Switzerland regarding the snow depth? Or is it a degrade, or let's say a decrease everywhere?
It depends, because we got stations that are quite high up in the mountains, and it's not necessarily, well, it's a overall, it's a, you could say that it's certainly not an increase, but during certain times, if you just look at main winter, say December, January, February, it could also be the other way around, so it could be a bit tricky.
There's one question from Eric Engström in the chat. He asks, how many automatic snow measurements do you have in Switzerland?
It's a good question, because I mainly focus on manual ones. But I would say roughly about 100 to 150, something like that.
Thank you. I can't see any more questions, so then thank you again. And then we proceed to the last presentation before the break, and that's given by Geno Resch from the University of Graz. So please, can you upload your share your presentation? Then you can go ahead.
So does it work? Do you see the presentation?
Yeah, I can see it and I can hear you.
Perfect. So hi everyone. As you can see, this presentation is also about snow, and already in spring in the valleys it has melted, but in the high alpine conditions, high alpine mountains, you have perfect conditions for crossing the mountains. But it can also happen that on the way down you have to carry them all the way, because maybe the slope is south faced or it's warmer, and it's not only changes in altitude but also between years. So in snow, in 1 year, in this particular example, it's in this year in January, you have like 70 centimeters of snow in southern Bavaria in Germany, but 1 year before, the same day, there's barely snow. So this can happen everywhere, and climate is what you expect, but weather is what you get. I really like that quote. And there's some studies that came out this year about snow analysis, and one particular I want to mention is because they analyzed more than 3,000 stations from Matthew et al., but only in rather a short time. So the observations that they used started mostly in 1971 and ended in 2019. And of course, the question is, why didn't they use longer stations? There are several answers to that, but one is because there's at the moment not really a well-tested homogenization technique for snow depth observations. And I'm working on a small project where I want to close that gap. I'm going to show you some results that currently came up. And one thing is there exist lots of stations that have long-term observations. In Austria, there are mainly 2 departments from the state that do long-term snow observations. One is the Zentralanstalt für Meteorologie und Geodynamik, the ZAMG. They have around 160 stations where snow observations are being done. and the hydrographic department. So they have around 700 stations and gathered all around Austria. And one big disadvantage from the measurements of the ZMG is that they have big gaps during the Second World War, because all of the observations were transferred to Germany and then in 1955 destroyed. But the hydrographic department, they have long-term and old observations, as you can see on the right side of this plot. So the darker the color, the longer the observation. And in Austria, it's interesting that the snow death observations are mostly older than the new snow observations. And in many other countries, for example, Switzerland or Italy, it is vice versa. So the new snow death, or the death of new snow observations, are older than the snow death observations. As Moritz already have showed, the observation methods are pretty simple and didn't change a lot in the last couple of years, or the last 130 years. So the majority is in Austria is still done manually, because the hydrographic service has manual observers. So around 700 observations in Austria being done daily with either a fixed snow pole or a snowboard, or as you can see in the middle image, you measure several points at the same time. But meanwhile, automatic stations have been built up. And one big advantage is, so this is an image from northeastern Greenland. You can build up a station and have snow measurements there where observations weren't possible before. So most observations are being done either manually or with ultrasonic or laser observations. So this is how a typical year looks like. In November, the observations start, and in May, the observations mostly end. So you have in the data lots of NA values and lots of zeros. And also it's an additive climate variable. So you have to deal with it a bit different than with variables like temperature or precipitation in the numbers. And you have also changes if there's melt, or if there is snowfall, but also just because of settling. So the unnecessarily melting, like here in February, but it can just mean that the snow settles slightly, which makes the corrections and also the quality checks a bit difficult, and some of them that have been applied to snow observations in the past weren't really good. There are lots of long-term seasonal observations. For this, you can see, of course, there are gaps, like, for example, during the Second World War. And as all climate variables have it, also snow observations have it. So the different colors show different locations or different observers. And of course, there are shifts. In this station, there's one shift or one break, and they can be detected and also should be. And at the moment, there are two papers out that did it, one with Prodige, one with the SNHT, and they produce quite similar results. But of course, it's a good idea to have a better look at it. And I focused on the corrections. So what we did was quite classical. We tried to find breaks, correct them with either a station network or with the single best station. So on the right side, you can see the plot with the correlation versus the distance to the station. And in most of the times, in most of the situations, the closest station has the highest correlation, but like in everywhere in all other climate variables, you should check also the reference station, because maybe there are breaks or the station itself has problems. And therefore, you can see on the right side also the orange triangle is the station that we selected as the reference station for the specific candidate. And I chose the example Rauris in the Hohentauern area in central Austria. So what we did was we tried to find similar climate. And with snow is very, how do you call that? Picky in terms of the stations or the station environment. Because sun and wind are the major influences. So in one valley, the snow conditions can vary completely to the different valley. Like in Austria, mainly north to south. So we tried to eliminate these influences by just making a network with the horizontal, the vertical distance, and the correlation. It turned out that the vertical distance was very important, and also, of course, the correlation. So in most of the cases, we chose the highest correlating station, but always took a look at the specific station conditions. Like if the station environment was different or largely different than the other one, which of course had an influence on the results. The homogenization method that was used some years ago was INTERP by Vincent et al. So it's a rather simple method. It takes the median of the candidate series after the break and before the break, and either as a reference series some single reference station, or also several stations that can be combined. In our results, it showed that there wasn't a real big difference, but in the last year, we tried to improve the correction method. So we chose the same method for the reference series, which was the highest correlating station. The results largely improved the quality of the series, but they inherit one big problem. The danger of overestimating large snow depth and underestimating very small snow depth, because the method works like this. It has, so this is a new method. The old method, it works like this. It has one correction factor for all values. So a snow depth of 150 centimeters is multiplied, let's say, by 1.2. And snow depth of 5 centimeters is multiplied by 1.2. And obviously, this produces wrong results. So the conclusion of the authors of the old method was not to use daily values, but seasonal or monthly mean values. And with that, the improvement was quite good. And in the last year, we tried to improve the method by combining INTERP, so the formula, but applied to different quantiles of snow data. So we, so the basic idea is to apply, so to have enough values for the calculations. So we chose 3 quantiles. So the 0th to the 74th, the 75th to the 95th, and then the 75th to the 95th, and the 95th to the 100th percentile. So it's not really what you see here. So it should be shifted a bit to the right. And then calculate a single correction factor for these quantiles, and then interpolate it. So this is the, on the x-axis, you see the percentiles, and on the epsilon axis, the correction factor. In red, there's the correction factor of the old method of INTERP, and in darker blue, the correction factors that have been calculated for the 3 quantiles. But if you would apply this method, if you have, so here and here, so at the interquantiles sections, you would have artificial jumps. So therefore, we just did a simple linear interpolation method from the center to of one quantile to the center of the next, and the upperst value and the lowest values use the directly calculated values. The numbers here show that we had quite some observations for having stable statistic results. That would change if you would adapt the upperst quantile from the 95th to the 100th, maybe to the 99th. Then you have only 50 observations in 30 or longer years, so it's not a good idea. And we also tried several quantiles. Like this is the method that turned out to be the best results, to deliver the best results. But we also used methods, variations with 5 or 6 or 4 different quantiles, or where the 0th quantile to the 90th was 1 correction factor, and then the 90th to the 100, and different versions. And this one turned out to deliver the best results. And for knowing what a good result means, 3 validation scenarios were created. In one, there was more snow before the break. In one, there was less snow. And in one scenario, we replaced the station. And for the validation, we used a newly created Swiss parallel data set, which was a pretty good idea for using that, because the stations are very close by. They are all of them roughly within the same village, and below 3 kilometers of horizontal and below 100 meters of vertical distance. And we took one series of this parallel data set and changed it and made some validation scenarios in. So we always used the Meteo Swiss station for a candidate and the SLF station in the same village as a reference. And with this, we were able to have a look which version of the quantile matching method was best, if it is better than the old method. And in the end, we came up with the product that I showed before. And we tried to analyze 3 different climate indicators. One is the seasonal mean snow depth, one were all daily snow depth, and one was, I called it HS95. So it's the very large snow depth from the 95th to the 100th percentile. And then we just counted the number of stations which were better in either the old method, which was interp, which is shown here in red, or interp quantile matching, which is shown here in blue. And luckily, the very large snow depth showed the strongest impact, of course. But also interestingly, the seasonal mean was most of the time slightly better with the old method, which only used 1 correction factors for all values. And the idea was also to have absolute error measures like the RMSE, and we also calculated the efficiency. And also have some relative error measurements, and the results were quite similar between the RMSE and the relative error measurement. And in some parts it was important to have also the absolute measurements, because the values were quite, the differences between interp and interquantile were quite small. But in the end, it turned out that the new method delivered much better results in large snow depth and also the daily snow depth, so about in 70% of the cases. And also the error reduction in the larger percentiles was quite good. So we came to the conclusion that the new method was better than, so interp QM was better than interp. So we applied it to 6 stations in an Austria snow depth dataset, where the break detection was already performed. And as you can see in black, it was the original time series, in red, the old method interp, and in blue, the new method. On the left example, Rauvis, there were 2 breaks. And as you can also see, the different correction factors had an influence that between 1973 and 1993, the values, the correction factors from interp was higher. And also in the years before, in the first break, the interp QM produced higher snow depth. In some stations, the correction factors were either above 0 from interp, or above 1 from by interp, and below 1 from interp QM. So in fact, the change of the corrections, the direction of the corrections changed completely. As a final result of this first part, we analyzed the impact to trends and the significance, and all stations in Austria had a negative trends or no trend. There were no stations with a positive trend. And of course, there's a difference between interp, which overestimated large values. So some stations overcorrected some stations. So they were significant. And with interp QM, so with the quantile matching, the results were a bit lower in some stations. In other stations, for example, in Oed, which was a very low level stations at around 400 meters above sea level, the significance was not there in the original data, but with interp corrected, but it's much more with interp quantile matching. So the next steps will be, to finish a paper about it, about the method. And it will be hopefully published in the International Journal of Climatology. So we will submit it in a couple of weeks, hopefully. And after that, we will also try to homogenize many other stations. So this is a selection of snow data. It's from the SNOWPAD dataset. It's publicly available. It's mainly, no, it's only stations from Austria. There's also some Swiss stations, but I don't know if it's publicly available. And this is the unhomogenized version. So some stations within there, as you can see around the northern part of the Alps, they have slightly positive trends, but to these new added stations, no break detection was done at the moment, but it's ongoing. And so most likely the stations that in this dataset now have a positive trend will change to negative or to no trend at all. But we don't know at the moment, but that's the work that we will do in the next couple of weeks and months. So thanks for the attention.
Thank you, Gano. So then I'll ask if there are any questions from the audience. I can't see it. Have you tested other types of homogenization methods than the interp method to this data?
Not at the moment. We thought about doing automatically homogenization with maybe AQUA, but let's see if it works out.
Yeah.
Because the underlying technique is quite interesting, and we were surprised that quantile matching results weren't as good as we expected it to be. So there's, of course, still research to be done.
Yeah. And I think that's also to try different methods is a kind of the validation process.
Yeah.
Are there any other questions? Doesn't seem to be. So thank you again. Are there any messages before we go to break, Thanos?
I would like to thank you very much again for chairing this session, Oday. Now we have a break, and we will in 34 minutes at 1300 Athens time or 1200 Central European. Go grab a coffee and see.
Okay, see you then at 1 o'clock or 12 o'clock over 11 o'clock, wherever you are in Europe.
Ole Einar, floor is yours.
Thank you. So welcome back to the second half of the session on homogenization at the EUMETNET Data Management Workshop. So the next presentation will be given by Jose Gerardo from EUMET, and he will talk about the value of reanalysis as reference to the homogenization of climate series, which I think is a very interesting and valid topic to discuss. So please, Jose.
Thank you, Ole Einar, and Kalimera to everybody. The summary of my talk will be after an introduction, and we speak about what data have been used for this exercise, both observed and reanalysis, the homogenization of the target series that would be used as a benchmark, the benchmarking approach. Then I will show you the results, basically root square errors and trend errors, and we can discuss some conclusions. Reanalysis have been used as a source of reference series for the homogenization of observational datasets with climatol when there were time steps completely void of data, a condition often found not only in isolated regions, but also in the first decades of the 20th century in many parts of the world. Although there are many examples of their use for the homogenization of several climate variables in Antarctica, Australia, Europe, for example, the homogenization of the ICAT dataset within the Indices project, and no evaluation of the suitability is generally made. For example, although the 1941 to 2016 daily peak wind gusts of more than 500 Australian cities were homogenized with and without the help of NCEP and CAR references, the lack of a trusted homogeneous dataset prevented the assessment about which of the two approaches produced better results. Reanalysis series are not completely homogeneous because of the different availability of observational systems along time, as when satellites began to provide data. However, they can be assumed to be more homogeneous in general than the observational series. Moreover, as no observed series can be presumed to be homogeneous, the homogenization of climate datasets composed by many series may take a long processing time due to the high number of iterations needed to gradually eliminate all significant inhomogeneities. Therefore, the use of a single reference series, which is the approach used by the RH tests, drawn from a reanalysis, would dramatically shorten the time of the process. This communication show is presenting a comparison exercise on the use of reanalysis series in the homogenization of temperature and precipitation daily datasets of an area of Spanish Duero Basin, both at the monthly and the daily scales. The station chosen as target for this comparison was Valladolid Villanubla, which is a small airport. Is located by the center of the Duero Basin in northwestern Spain. And so their daily series of extreme temperatures and total precipitation were used as target series for this test, introducing random biases and homogenizing them with the help of neighboring stations or with 4 different reanalyses. The observed series of Valladolid and reference series up to 25 kilometers apart, which amounted to 12 thermometric and 22 pluviometric stations in total, were taken from the EUMET climate database. The reanalysis series of ERA5 and climate forecast system reanalysis were obtained from this address, the portal of Climate Engine, for the point of the coordinates with the Valladolid Villanubla station, while 2 other reanalysis series, that is the 20th century reanalysis version 3 and NSEP-MCAR, of the closest grid points to this observatory were downloaded from this other portal here. The period chosen had to adapt to the time span, to the availability of the series of reanalysis, and therefore it was limited to the 37 years comprised in 1979 to 2015. So, first homogenizations of the monthly Valladolid, the daily series were aggregated into a monthly series in order to have a more reliable homogenization. And this is the comparison of the number of outliers, the breakpoints, and SNHT and root mean square error values obtained after the adjustment. This is for maximum temperature in the center, minimum temperature by the right precipitation at the monthly scale, I remember. And then with only neighboring stations, or with only one of every of these 4 reanalyses that had been tested. You have here the number of outliers. There was only 1 outlier was rejected with this reanalysis. The number of breaks detected and corrected. 1 here, also for everyone, for maximum temperature, minimum, and precipitation. With neighboring stations, there was a 1 breakpoint. And with reanalysis, only for maximum 1 detected with ERA5. In minimum temperatures, there were more detections, 1 with ERA5 and 2 with NSEP-MCAR. And no breakpoint was detected with reanalysis for the precipitation series. But anyway, the breaks or the dates of the breakpoints were very different. Only the minimum temperature and the precipitation detected with neighboring stations can be considered to be the same, and all others are quite different. So after having adjusted or homogenized the monthly Valladolid series, the daily series were adjusted using the breakpoints detected at the monthly scale as metadata. And then here I present the outliers and again the SNHT and root mean square errors after this adjustment. For the adjustment with only neighboring stations, there was one outlier, the only one at the daily scale that was rejected for maximum temperature. And here you have a variety of SNHT and root mean square errors. You see that the beta adjustment, or at least in terms of SNHT, would be the NSEP-MCAR, But for root mean square error, the best for maximum temperature was with the neighboring stations. More or less the same is happening with the other two variables, minimum temperature and precipitation. Here, the ERA 5 reaches a slightly better root mean square error, while for precipitation, also the neighboring stations are producing the lower root mean square errors after the adjustment of the daily series. You can see very different values for SNST after this, but well, you see a variety of results. And then I'll go to the next slide. And then we are going to use this homogenized Valladolid series and to introduce them by introducing inhomogeneities into this series. They were perturbed with 1 to 3 with the same probability biases of normal distribution with 0 mean and 1 standard deviation in degrees centigrade, while the precipitation series were altered by factors drawn also from a normal distribution with mean 1 and standard deviation 0.2. That would be 20% biases in the precipitation series. So there was a multiplicative approach for the precipitation series and additive for the temperature series. These problem series were homogenized using references either the neighboring observing stations of every reanalysis series, only one at a time again, with the climatograph package as in the previous homogenizations. This procedure was repeated 100 times for each of the settings. Root mean square errors and trend errors of the comparison with the true solution are shown as box plots in the following slides, with annotated correlation coefficients in the root mean square box plots. These are the results for the monthly mean temperatures. Here you can see how, in red, you have the errors introduced by the introducing the homogenization, the inhomogeneities, the biases in the true series, the one that we have homogenized and we are taking as reference. And you see, so this is the problem station, the errors of the problem station. And here you have for neighboring stations only, for the century climaphoric system reanalysis, ERA 5, 20th century reanalysis, and second card. And by the left for the maximum temperatures and for the minimum temperatures to the right. You see that the best results in terms of root mean square error are again obtained with the neighboring stations, but the reanalysis are also producing good adjustments, lowering a lot the original errors of the problem series. And the same happens with less difference with the observed neighboring stations. The same happens with the minimum temperatures, except curiously with the second card, which is giving higher errors. The same for monthly, daily, yes, this is for daily the same, but for daily temperatures. And for daily temperatures, again, differences are not so great, not so big between the observed neighboring stations in relation to the homogenizations obtained using the reanalysis of references. But again, the results are a bit better for neighboring stations, for observed series, especially in maximum temperatures. In minimum temperatures, differences are not so high, but again, N7 card is giving worse results for minimum temperatures. I wanted to relate this, I go to the previous one. Has this any relationship with the correlations between the series? And yes, we see that the best correlations happen with the neighboring stations. And then there are for the reanalysis, correlations are lower, but differences are not so big. So it's not a keystone, very, which would be the definite criteria for choosing one or the other. With minimum temperatures, we see that maximum correlation is also, although lower than with maximum, also for the observed stations, while here we have the lower correlations, but still quite high. Especially, you can see that between 20 CR reanalysis and N7 card, correlations are very much the same, although results are quite different. And for daily, we have here that N7 card has the lowest correlation, so the worst results. And always the same is more or less repeated. The best correlations are with the observed stations, and the other reanalysis have lower correlations, but still the root mean square errors are much reduced in comparison with the problem series. Now for precipitation, to the left with the monthly and to the right for the daily precipitations, the box plots are very similar, very similar, only changes the scale because the monthly precipitation, the root mean square errors are greater, while for the daily, they are very low, but this is due to the fact that most of the daily precipitation is zero, so this contribute to lowering a lot of the root mean square errors. And we see that here it is more relevant, the difference between the observing neighboring stations compared to the reanalysis. The reanalysis are still reducing the original errors, but not so much as it happened with the temperature series. And now we go to compare the trends. These are the trends for maximum temperatures. The less biases are obtained with the neighboring stations again. But the other, the range of trends is much more reduced, as is the normal situation after homogenizing the original series. And here we have also the same, that with minimum temperatures, the bias of the N7 card are the highest, while 20 CR have a bias very good, even is more reduced than with the observed series. Going to the daily extreme temperatures, the box plots are practically the same, so comments are valid for both time resolutions. And the trends for precipitations, we have trends errors here. The biases are perfectly corrected with neighboring stations, and all the reanalysis are giving lower trends than the original series. The best situated would be the 20 CR reanalysis. So we can go to the conclusions. Reanalysis are a good option to provide reference series for the homogenization of climate series. It also solves the problem of using composite reference observed series when there have been simultaneous changes in the network. However, well-correlated neighboring stations produce better results and therefore are to be preferred if they are available, which is not always the case. Due to its long time span and relatively good results, the 20 CR series seemed the best option to homogenize series beginning in the 19th century or first decades of the 20th, combined with ERA 5 series to provide references for the more recent years, because 20th century reanalysis, the version 3 stops in 2015. Current work, it would be interesting to add tests using more distance, that is less correlated stations, to compare the observed series when the correlations are not so good with the results of the same reanalysis series. That's all from my side. Thank you for your attention.
Thank you. So, are there any questions from the audience? So please raise your hand, or you can put a question in the chat if you like. I don't see any. I have one question. When you have tested 4 different reanalyses, could it be a possibility to put all those 4 into one basket and use them as a reference network instead of using single realizations?
Yeah, that could be added to the current word to the current web. Yeah.
But and also then test different reanalysis for inhomogenities against the 3 others, for example, just to have a kind of.
It would be good to compare results, because you will be using this in Norway, I assume.
Yeah, I think you in your abstract you pointed out that remote areas like the Antarctic or in the Arctic, where we have very few stations, reanalysis is one of the few options we have if we should go to try to make an assessment of the inhomogeneity or inhomogeneity of those remote series.
Yeah.
Because it might be several thousand kilometers to the next candidate station. So.
Yeah. And also, as climate are different, that could be also very, very useful to compare results.
Yeah. I don't see any other. There's a hand, Thanos.
Hello, Einar. Jose, I would like to ask you, could you briefly describe the topography of the area where the stations you selected? Topography, or is it hilly, or?
Yeah, it's in the center of, well, the basin is surrounded by mountains, which is the normal in basins, but in the Valladolid area is more or less quite flat, although there are some hills. Yes, it's a bit hilly, but not very much. So that's the reason why correlations are so good. And then I will try to choose in the same basin, but more distant stations in order to have less good correlations.
So more or less all the stations you used are in similar altitudes. Right?
Yeah, similar. They are.
Thank you very much.
You're welcome.
So thank you. Are there any more questions? I can't see any. So thank you again, Jose. And then we'll move further north to Sweden and to talk about homogenization of monthly temperatures of the Swedish observation network for the last 160 years. And the presentation will be given by Erik Engström. So please, Erik, the floor is yours.
Thank you, Ole Einar. I hope you can see my presentation now.
Yes, we can.
We'll just find the different screens here. So yes, thank you for this opportunity. I will present the work of my colleague Magnus Johansson, who could not participate in this webinar. And it's about homogenization of Swedish temperature data. So let's see if I can change. Yes. So the sorry, I also apologize if it's some noise in the background, because they're renovating our office house here in the institute, but I hope it will not be too disturbing. And so the prior homogenization work in our institute was to homogenize 35 Swedish stations that was manually merged and manually homogenized with the standard normal homogeneity test method. And the most important application was our climate indicator to show the temperature trend in Sweden. And now the new method that my colleague has developed is we use monthly mean temperature, and is from the start year of 1860 until last year, 2020. And we could use almost our entire network in Sweden in the homogenization, and that because Magnus has developed a new automated version of the interactive Homer method. Then we could homogenize a very large network with this. So we started with almost 1,000 data series with the lengths between 1 to 160 years. And in Homer demands at minimum 15 years. Time series that are shorter than 15 years, we sorted away and didn't use. And then Magnus Johansson developed the automatic coupling method or merging of the data series. And there were some criteria we used, that the horizontal distance should be less than 25 kilometers and the altitude difference less than 100 meters. And the correlation should be higher than 0.9. And if the overlap was more than 15 years, then we used the stations that did not merge them, so we didn't lose so much data. We wanted to use as much data as possible. And then also we classified the station as inland or coastland or island stations, and they were not possible to merge stations in different classification. So, and now to the left, you see in yellow the original series, and we have the number of series on the y-axis, and on the x-axis we have the number of series. And you see that we have a lot of short series, and the black dotted line is 15 years cutoff for Homer. But then we merge the series, and you see the result in the light blue color. So we get the number of series go down a bit, but we get longer series. So from 700 over 700 series, we merged them together to around 450 series that were then used in the homogenization. And to the right, you see the number of series for each year during this 160 years time period. So in the beginning, in the oldest times, there were about 20 stations, and then in the most recent years, a little bit less than 300 series. And here is an example of the automatic coupling merging of the series. To the left, we see merging of a number of short series. It's Skara in the mid-southwest Sweden, we can say. And you see that it's 5 different series that is coupled together to one series. And in the lower left panel, you see the position in Sweden of the different stations. And in the right figures, you see 2 longer series in Uppsala that is merged. And yeah, you see also the position of the stations in Uppsala in the lower right panel. So, and the newly developed method is published in a paper by Johansson this year, where it's also compared with other common methods. And in the automated interactive mode of Homer, some input parameters are used that can be used before the start of the process. And it is possible to use metadata also. And it can be run in batch mode, so you can set up a number of experiments and run them in parallel if you want. And you can use different ways to choose the reference areas also in the method, like correlation or proximity or full coverage also. And here we see an example of a selection of the reference stations. So in the upper figure, the uppermost black line is the candidate station and the data coverage for that station. And it's a bit hard to see. I think it's maybe Gällivare in the north of Sweden. And then you see in the other colors of lines below the black line, the other possible reference stations and the data coverage of those stations. And in the lower figure, you see the position of the other stations around the candidate station. And here we see the result of the homogenized data. So it's 5 different stations from the top: Falun, Gävle, Malung, Sandviken, and Vassebo in the bottom. And the original data is the purple color, and the old homogenization with the standard normal homogeneity test is the green one. And you see that Falun and Gävle, the two on the top, is homogenized in the old homogenization. But the 3 stations in the bottom is not a part of that old homogenization. And the pink color is a new automatic Homer homogenization. And the vertical lines, dotted vertical lines, is where there either is a metadata notice of a possible break, or where the different methods have detected breaks. And so you see that there is a lot of breaks detected and noted in the metadata. And the difference is not very large between the raw data and the homogenized data in these examples. And here we see a resulting climate indicator for Sweden for the temperature, where we have used now instead 39 stations compared to the prior 35. So we have added 4 more stations. But as I said on an earlier slide, the total homogenized data set is around 450 stations, but these are the longest time series we have in Sweden. So that's why we use them in this example for the climate indicator. And here we also see in the figure, the black line is the raw original data. And then we have Homer is a green line, and the old homogenization SNHT is a blue line. So we see that the new homogenization will give a stronger temperature increase. It's maybe a difference of 1.2 degrees during this 160 years. So it's a little increase temperature trend as a result of this change of method. So the conclusion that we have implemented a new method to homogenize the monthly mean temperature in Sweden for the time period 1860 to 2020. And there were 769 series automatically merged to 449 series that were then homogenized with this new developed automatic version of the interactive Homer method. And it indicates a faster, stronger warming in Sweden than we have shown before. And what do we plan in the future is to also homogenize the daily temperature, the monthly mean of also daily maximum and minimum temperature. And then we need to continue with precipitation. And we have an ongoing project now called Wind Gust, where we work with the wind data. And we will probably compare the Homer result with homogenization done with Klimatool and AQUA also, so we can compare several different methods. So thank you for your attention, and I'm happy to answer the question I can answer, or otherwise you have to email Magnus to get more details.
Okay, thank you, Eric. So, Jose, you have a question, I assume.
Yeah, thank you. Yes, my question is whether this development that you've made of making a completely automated version of Homer, is it freely available or not? Because if it was, it would be good to put in the catalog of freely available homogenization software packages. Thank you.
Yes, we're to share the scripts or the methods, so we can discuss that, how to do it practically, Jose.
Okay, thanks.
Are there any other questions for Eric?
I see Peter.
Oh, we can't hear you.
You can't hear me?
No, I can hear you.
Yeah, okay. Peter asked for the reference to the paper, so I can look it up and put it in the chat in some minutes.
Okay, thank you.
Thanks.
Yes.
I have thanked only to Eric. This answer.
Okay. I have one question, Eric. The difference in trends, or the signal that you presented in one of your last slides, the difference between the SNHT and the Homer results, is that due to the algorithm, or can it also be due to that you have different reference series, or are they then on the same reference data?
That's a good point. It should be, the figure should be based, of course, on the same station data set. So, but I don't know by heart now what Magnus used for that. If he, as you say, if there are different number of stations, it can be an effect of that also. But I should assume that he has used identical data for station data for the figure. Yes.
Okay, thank you. Do I see any more questions? If not, then you can send them directly to Eric, or you can send some emails to Eric or Magnus. So that concludes the presentations of this session. So now we open up for a more general discussion on homogenization. We had some talks on this morning about the AQUA software, and then we had presentations on precipitation and snow before the break, which I found very interesting to see, the homogenization of snow data, especially because that's something that we haven't dared to try here in Norway, at least, because there are so many local variations and there are not very high correlations. But should we discuss a little bit the snow when we are analyzing snow, we are very much using the snow water equivalent as a measure instead of snow depth, because snow depth is it's very, there's a lot of local variations also due to wind redistribution of the snow. Have you, I can ask, yeah, Moritz is put his camera on. Do you have any comments on that, or Geno?
I can comment on that because the reason why we used snow depth is basically just due to the availability, because we have snow water equivalent measurements, but not as many as we have snow depth measurement. And that is because in Switzerland, the focus for measuring snow depth is basically in view of the avalanche situation, and then the people are basically interested in the amount of snow and not in the priority of the snow water equivalent. So it's basically just due to the availability that we use snow depth.
And the approach or applicability of the data.
Yeah, in the case of the snow depth, also the correlations for snow depth are much higher than for depth of new snow. For example, for I think all of the stations, when you make a diagram of the correlation versus the distance, the correlation declines very slowly for both, for many stations, but it starts at a lower level around 0.5 or 0.6 for new snow, and around 0.8 or 0.9 for snow depth. But we didn't try snow water equivalent yet, but there's a paper out, I think it came out last year, about how to use snow water equivalent for new snow modeling. So in our case, mainly it's because of the correlations, not because of data availability, and also because the correlations between the one and the next valley are much higher, even on daily scale for snow depth than for new snow. So the daily variation is so the work that I did basis on work from Roland Koch from the ZMG, and he said in his opinion the homogenization of new snow is almost impossible at the moment, at least at daily scale.
What about a little bit regard to the talk by Jose? Instead of using station data only, what about using remote sensing products as a background or as a reference? Is that something that you have considered?
We tried a snow model for gap filling, the snow grid CL from the ZMG, and it works quite well. But I don't know any comparisons at the moment between really good gap filling and snow models, because the gap filling with either snow modeling demands a lot more data, and also if the data quality is good, then also the outcome is good. Of course, yeah. And I think that's the main problem at the moment. But for Austria, the snow modeling is quite good. But so at the moment we didn't try it with the new data, but there were some tries with gap filling comparisons, and it was quite good. But mostly the gridded data starts with 1961, and if you want to go earlier, so many snow observations from the Hydrographic Service start in 1895 or 1900, and there's no radiation data, or at some points there's temperature and precipitation, but if the network is scarce, and you also have to homogenize that first. So yeah.
Yeah, then you have a problem.
Yeah.
I just see in the chat that Eric has put out the reference to the paper he mentioned in his presentation. So for those of you interested in that, you can go to the chat and download it. Are there any other comments? If we go slowly towards using reanalysis data or remote sensing data as reference data for homogenization, are there any comments on that? Mary, you have your hand up.
Sorry, it takes a second to unmute. My question is, for those who just homogenize on a monthly scale, how do they handle indices when they know that there's breaks in the series? Do they just not produce indices where, daily indices where they find the station has a break, or how do they handle it?
Floor is open for answering.
I'm not sure if I understood the question well, but it's about adjusting the breakpoints detected to the real dates of the metadata.
Yeah, if you only do your correction on a monthly scale and don't apply a daily correction, then for climate indices, how do you handle those? For, say, rainfall, if you've got wet days, dry days, tropical nights, for temperature, things like that, do you just leave out the series that have breaks in them, or do you apply correction? Because it's going to be different in some cases.
Yeah.
So how do people handle that? I mean, at the moment in MET-EARN, we haven't got daily data, so we're working on it at the moment. But in the past, we just used raw data for our normals and then, for days, wet days, etc., for rainfall. It was just based on raw data rather than homogenized data. So I'm just wondering how people who only do monthly data handle it.
Yeah, what I do with climatology as the detection at the monthly scale is giving you breakpoint dates referred to the first day of the month. And if I have metadata, I can edit the list of breakpoints and edit the dates and change them to adapt to the metadata if they are reliable enough. And then I make the adjustment of the daily values with the corrected dates. If I don't have metadata, I also make the adjustment with the breaks detected at the monthly scale.
Peter, you have your hand up.
Yes, I also would like to give a response. What does AQMANT? If the input is on monthly scale, AQMANT does everything on monthly. There is no option to conclude a daily resolution. If the input is on daily scale, the user can select a monthly or daily input, or monthly or daily output, or both. And what is the situation if that data gaps occur? The input in theoretically on daily scale, but data gaps occur, then the AQMANT does automatic gap filling. But there are some limitations how one can use and for which purpose it is recommended to use such gap fields. It is clear. Thanks.
Thank you. Do we have other comments or questions or problems that we would like to discuss? If not, I think we'll stop this session here, and then we take a short break before we start again at 2 o'clock Athens time.
Excuse me, I think I saw that Peter Domonkos has.
Mari, you have your hand up.
Yeah, sorry.
Yeah, okay.
Yeah. Sorry, one last question. With the Snowdeck study where they used AQUA, Climatol and Homer, and they're only correcting the breaks for where you have two methods give the same break. For the actual correction, what methods are they going to use for correction? Have they decided yet?
It's to answer your question, no, we haven't decided yet, because we only are at the stage of evaluating the detected breaks, and that is definitely the next step to sort of to try to find a solution for that, because at the moment we're not quite sure which method we want to use, and unless we decide on that, we can't decide on which correction methods we want to implement.
Okay, thank you.
Okay, thank you. So Thomas.
No, I thought that Peter Domokos had wanted to ask the question, but I don't.
I simply left my my hand at that time.
Okay.
Okay.
Thank you. So, Ola, Einar, I thank you once more for sharing this session.
I have one final comment on there, and that's just to advertise a little bit for the homogenization colloquiums that is going on. That is organized by Victor Venema and colleagues, and the next one will come up probably in the late January or early February next year. So just keep your eyes open, and then we can continue discussions there. So so I would so I would just like to talk to thank all the presenters and all those that had questions and comments, and say goodbye from Oslo, and then I'll give the word back to you, Thomas.
Thank you very much, Einar, once more. We'll circulate the information about the homogenization to everybody who's registered to. We break now for 10 minutes to reconvene at 1400 Athens time. Very much again.
Good afternoon, everyone. Welcome to session 6 of this data management workshop. My name's Dan Hollis, and this last session a little bit different to perhaps some of the other sessions that we've had in the last couple of days, or even in previous workshops. So the focus this time is on energy meteorology, and we've got 2 talks for you, followed by an opportunity for some discussion. So our first speaker is Frank Kaspar from Deutsche Wetterdienst, and he'll be talking about the use of reanalysis in services for the energy sector. So Frank, when you're ready, thanks.
Yeah, I'm ready. So I have to open the PowerPoint document. Where is it? Sorry.
While you're doing that, just to remind everybody, if you want to write any questions in the chat, that's fine, or you can ask the questions at the end of the presentation.
Okay, I hope you can see it now.
Yes, I can see that.
Okay,
it's good.
Great. So as Dan already said, so this is kind of a new session for this data management workshop. And you know me already from Monday. On Monday, I talked about our activities in climate monitoring for Germany. But we have also seen that there is a new and increasing need for additional data sets, especially from the renewable energy sector. So, and I will talk a bit about our activities in that field. We had a presentation of Semyon Chimanke on Monday. He was talking on the reanalysis activities of the Swedish Meteorological Service and the C3S consortium. So to some extent, my presentation is similar to his presentation. So the German Meteorological Service is also working on this reanalysis topic, but my focus is on the applications in the energy sector, and therefore I submitted the abstract to that session here. And so I will first talk a bit about the reanalysis itself. It's similar to other reanalysis. It's just built based on our regional NWP model, and I will then focus on our experience with applications in the energy sector, and would be interested to me to see if that you have similar requirements in your nations. So the system itself, it is based on our NWP model Cosmo that was used here in a resolution of 6 kilometers. The development has happened already some years ago together with the University of Bonn and Cologne in Germany. So they helped us to do the basic research to really see if this approach is feasible. And the idea is to just operate the model together with the data assimilation mechanisms for like 20 years or more. So the data set I'm using in the following is based on a period starting in 1995 until 2019. We stopped with the production that year because this reanalysis was based on the ERA interim dataset, which is not available anymore now. But we are currently setting up a new system that will use ERA 5 boundary conditions, and then we will regularly update the dataset. So the basic idea is to assimilate all the data that is also used in the numeric weather forecasting, and to use the same model version consistently over time to produce a homogeneous data set. Of course, there might be some impacts on the homogeneity due to changes in the observing system, but the model itself is consistently used in the same version for the production of all these years here. The data set is openly available, so you have the links on this slide, and therefore we have also seen external applications of the data set. So, I mean, this is the basic idea of the reanalysis. So you have the continuous assimilation of observations, and therefore this helps you to make sure that your simulated atmosphere is kind of near to reality, and therefore a realistic representation of the weather patterns in the past. Well, there has also been a 2-kilometer product, which with a focus on Central Europe. So, of course, in our case, with Germany in the center of the domain. There are also some applications of this 2-kilometer products, but here I will mainly talk about the European product, which has been produced with 6 kilometers. The name is Cosmo RIA 6. Therefore, it's a blue domain here. So as I said, a number of products are openly available, and one clear advantage of the reanalysis is that you have a consistency between a wide range of parameters. So of course, you have to look at the quality of each individual parameters, but at least it's produced with one system, and therefore the data sets are physically consistent. And so we have applications from the wind energy sector, but also from the PV sector, so photovoltaics. And in that case, you are not only interested in the surface radiation, but for example, the production of the PV modules, the energy generation also depends on temperature, and the temperature of them depends on the wind speed in the surroundings. So you have a dependency on additional parameters, and these are the typical cases of applications where you are interested in the consistency of these different parameters. So as I said, the dataset is openly available, so the users can go to an open data server and just download the raw files, but then they really have to handle the large amount of data and the original data formats as they are produced by the NWP models. But we have seen that there are a lot of applications, some of them also published in the scientific literature, and for this is just a selection of them. Here you see in the titles that a lot of them are addressing questions in the wind energy sector. And last year, that is the link on the bottom, I and my team, we wrote a paper with a review of the existing applications. So we try to look at what have people done with the data set and what is the focus of the applications. And what we saw that the majority of the applications came from the energy sector, although there is a potential to also use these data sets for hydrological or question of vegetation, agriculture, forestry, or so on. So all these models would benefit from this consistent availability of parameters. But in practice, we see that the majority of applications is from the energy sector, often in the wind energy sector. They are directly using the data, but we also have the, sorry, I just forgot a slide, it seems. So we also see applications related to solar energy. In that case, the papers are often written in a somehow different way, because the wind energy applications, they are just interested in the data and they don't have relevant alternatives to it, so they just use it. But in case of solar energy, you know that there is a range of potential data sets, so they could be derived from satellite products or based on ground-based products, so interpolated gridded data sets, and therefore the papers that are addressing research related to solar energy, they are often just starting with a validation of the data sets. And it's interesting for us to see that this is a benefit of the open data policy also. So we get a lot of studies that are done by external people, but they help us to also understand the quality of our data sets. And now I would start to talk about our own applications in the energy sector. So the German government is planning to increase to build a number of offshore wind parks in the Baltic Sea and the North Sea. So here you see like a map of the so-called exclusive economic zone. Though this is a zone in the North Sea and the Baltic Sea where the German government is responsible for the planning, and so we have similar conditions in other countries here, and the government defined their plan how much capacity should be installed until 2030. And so the DWD was asked by another government agency to support these investments by providing reliable data on the wind conditions. And as large amounts of investments are done here, so we of course have to understand the quality of the data set and to be sure that we really provide reliable data to these users. Therefore, a number of applications or evaluation studies have been performed, so I cannot go into all of them. But again, I would like to point, if you're interested in that, there is this review paper from the last year, and it has, it's at least summarizing the results of all the individual studies. So here I'm just picking out some specific examples. So some years ago, we had a cooperation with a number of other meteorological services in Europe, and they were also developing regional reanalysis systems based on their own NWP models. So what you see in the plot is a comparison of the individual regional systems with also ERA interim, which is a global reanalysis that has been used as boundary conditions here. So we used the German wind measurements to analyze the quality of the wind data produced by these reanalysis systems. And the higher the value is here, the better the quality is. So you see that the different colors are indicating the regional systems, and they are typically significantly better than the global product, which is shown in gray. You see slight differences between these systems. So we were quite happy to see that the blue one, which is our own system, is of quite good quality here. But you could also argue that, of course, the German NWP model is somehow tuned to German conditions, so it might look a bit different in other regions of Europe. Okay, this work that I've just shown was done a few years ago, where ERA 5 was not yet available. So, of course, people were interested to see how does a new global reanalysis of the Copernicus service compare to the previous one. So here you see a similar comparison of our own system compared to the two other global reanalyses in orange and gray. So you see that also the global systems made significant progress here. And therefore, we hope that the next generation of our own regional product will also benefit from these improved boundary conditions. But this is currently under development, so I cannot yet comment on that. Of course, when you're going to consider using the reanalysis as an alternative to your station data, you also have to consider well, a number of specific details. So what we see here is a comparison of two stations that are quite close together in Germany. But when you look at the histogram, then you see that for Mannheim, the simulated and the station data agree quite well, but you see a significant difference for the other station. And the main reason for that is that the height of the station. So if the grid cell of the reanalysis is at the same level as the real station, then the agreement is quite good, but there might be differences, and you have to consider this in your applications or try to correct or somehow for this effects. Well, as I said before, I'm not only interested in the land stations, but also on the behavior over the sea. So we have here the histograms of the hourly data compared to some masts that are installed in the North Sea. Here's one example. It's called Fino 1. It measures the wind speed at a height of 100 meters, and these data are not assimilated in the reanalysis system, so it's independent data, and we were quite happy to see that the agreement between the simulated and observed data again in the histogram is quite good. So we consider it as a relevant data set to provide information also in the context of these investments into offshore wind energy. But there are also disadvantages when you look at some other details. So, for example, this is a comparison of a mast which is located in Lindenberg, which is one of our specific observatories. Again, measurements up to a height of 100 meters. Here we looked at the daily cycle and, well, near to the surface, it's represented quite well, but when you go up to higher levels, then you see a difference between the observed and the simulated daily cycle. And well, again, I just want to point out, you have to consider this. This is specifically relevant for your application. So in case of the daily cycle, one thing that is interesting for us is if you combine solar and wind energy, then how do these cycles on the daily scale, but also on the annual scale, compensate each other. So at the daily scale, you have to be careful with the data, but on the annual scale, the quality was quite good, and therefore we also had a study. Personally liked it very much, so it's produced some very obvious plots. So for meteorologists, it would probably be obvious, but for the general public, they were quite interested in seeing that. So we calculated the wind energy and the solar energy and compared also the temporal behavior, also looked at balancing effects and so on. And the interesting thing is that you have this annual cycle in wind and also in solar energy, which is shown here in blue and in red. But when you combine it for Germany, at least, you see that the sum of it gives you a quite homogeneous production over the year, which is a good argument, well, to discuss energy scenarios for the future. The data, as I said, the data set also covers Europe, so we could do the same analysis for Europe, and again, similar results here. So also on the European scale, you would have that benefit when you combine both energy sources. This is just some arbitrary examples out of our work where we use the data set to answer some questions that were addressed to us from our well, other government agencies or partners, and well, therefore I would come to my conclusions now. Well, it is a data set that is available for more than 20 years, has a spatial resolution of 6 kilometers covering Europe, and several parameters are available. The data set has been evaluated, and we were able to demonstrate advantages compared to global reanalyses. It is freely available, has been used in several applications, and we are currently working to prepare the next generation. In the NWP activities, the DWD moved forward to a new system. It's called the ICON model, and it has a completely new approach for the data assimilation, and therefore we have to see how we can produce regional reanalysis based on that system. It well has some significantly increased computing requirements, but it will also allow us to provide additional information about the uncertainty of the data sets and so on in the future. Yeah, that's it. Thanks.
Okay, Frank, thank you very much. That was a very interesting presentation. Do we have any questions for Frank, either in the chat or if you want to raise your hand and ask Frank directly? I'm not seeing anything. I guess I can. Thanos, yes, I was just checking for raised hands. Yeah, if you have your question, yeah, please.
Yeah, Frank, thank you very much for your very interesting presentation. Indeed, I would like to ask, in order to get the data, is there any kind of registration necessary?
No, it's an open data server. When you have the address, you can directly go to the. You have seen it in my slides. It's for direct download. So you have the grip files that are produced from the model. You have to care with a number of technical details. For example, it's produced on a rotated grid, but we added some PDFs that explain how to handle the data. But there is no restriction on that. Even you do not have to register.
Thank you very much.
And that is also the case for the other climate data from Germany, actually. So since a few years, we have an open data policy, and you also can directly access our station data and gridded products and so on. I see someone in the chat, I think.
Yeah,
Gerard, I tried to upgrade him to promote him to panelist, but
so he's asking about if there is feedback from the German government on the usefulness of the data set.
Well, somehow DWD is part of the German government, and also the other agencies, of course, are officially part of the government. Therefore, we have this cooperation with the agency, which is called BSH, is responsible for the north and offshore activities. So they are quite happy to get this data set because they are officially responsible to provide all the information on the offshore conditions to the investors. So that is not only a climatological information, but that is a number of very wide range of additional data sets. I think KNMI has similar activities in the North Sea. And well, they liked it really that they see that there is published literature that is documenting the quality of the data set, and that they can really understand what is the background of all this. So it's not only the usefulness of the data set, but often it's also the well, the openness of information, availability of evaluation results. Also, one argument was also that this is available in the peer-reviewed literature. So it was actually interesting also for me to see that those are not natural scientists, so they are responsible for the official decisions. So, but these lawyers and so on, they really understood what we were explaining to them, and they considered in the total approach as very helpful.
Yeah, thanks, Frank. So that is really helpful. So the background of the question was a little bit that in the case of the Netherlands and KNMI, there is some involvement of the Ministry of Economic Affairs in this. And although the KNMI is not part of the Ministry of Economic Affairs, there is some interaction between these two, and sometimes this is rather difficult. And I was wondering if there are similar experiences with the German letter service in trying to attract the right ministry.
Well, I have just talked about the positive points, but there could also be a long list of problems that I could address. Would be probably too long for today, but well, we can get into contact on that.
Brilliant. Okay, thank you, Frank. Do we have any other hands or questions? I don't see any others. One quick question from myself then. I think you said at one point that when you were looking at the daily cycle, that the agreement was better near the surface rather than at higher elevations or higher heights.
Yes,
and that surprised me. I'm not really an expert at all on reanalysis data, but naively I might have expected the agreement to be better away from the surface, where you don't have extra complications of surface roughness and the effects of topography are reduced, I guess, depending on where you're sited. And on another slide, you showed very good agreement with the offshore mast at 100 meters, but then the daily cycle is not quite so good. Is that right?
Yeah, that was my point. I mean, my plan was to openly talk about advantages and disadvantages of the data set. So in some cases, you have to be careful.
Sure.
Our assumption for the daily cycle over land is that probably the model has some issues with simulating the daily cycle of the low-level jets.
Oh, okay.
You can think on a number of things to improve that. We hope that there will be an advantage of the next version, but it might also just depend on the vertical resolution of your simulation. So you might just improve it by increasing the resolution. And one point could also be that you assimilate a lot of data which is observed near to the surface, but you don't assimilate so much information at the other heights.
Okay, yeah. Okay, good. Thank you. Right, okay. Well, I think we should move on. Thank you, Frank, for that. So you might need to stop sharing your screen, Frank, if that's okay. Thank you. So we'll move on to our next speaker, which is Peter Stepanek, and he's going to tell us about, again, this is for the power industry, and again about meteorological services in the Czech Republic. So Peter, if you could share your screen, that would be brilliant. Thank you.
Okay. So good afternoon. I hope you see my presentation.
Yes, I can see that. Thank you.
Thank you. So I will present our activities in the field of energy meteorology and our experiences in the Czech Republic. Well, this was meant as a poster, so I will show you only a few slides, and other details you will be able to find when you download the poster from the web pages of the conference. And one more things to add, this should have been presented by my colleague Pavel Zahradníček originally, but he's off, so that's why it's me. I will speak about this. So these activities, I will present what we do at the Global Change Research Institution. It is part of Czech Academy of Sciences, together with a private company, Ampere Meteo. Well, I wanted to change the slide. Okay. Well, so we start with weather forecasts. Then it's needed to run some post-processing like bias corrections of models. And then we create some products for energy companies. We create forecasts from several hours ahead, what we call nowcasting, to 5 days ahead. And we predict electricity production, but also consumption and even gas consumption. What is needed to say that in this field you need to compete. So for instance, during the last year, there was a great competition of several companies, even from abroad. Now I speak about E.ON company. So there were 2 Germany, 1 Spanish, and 1 other Czech companies, and we were able to beat in most of the parameters our rivals. Our approach is using what we call multi-model approach, because if your prediction is based only on 1 model, the problem is it is encumbered with some level of error and uncertainty, but by combination it's possible to reduce the error. In our case, we use IFS model from ECMWF, then Czech model Aladdin, then models from Metofis, GFS, and Arpège. Some of the models are free of charge. From some of them you have to pay. Actually, this year we also experienced with Cosmo model that was mentioned in the last presentation. And on the left bottom chart, you can see individual predictions, combinations, and the reality. So it shows that by combination of the models, you can reduce the error by almost 10%. And we further use the error by meteorologist intervention during the day. What we devote to is also correction of the models for a given location, because there is a specific bias of the models which is dependent on hour of the day and the space. All of the models we convert from their native resolutions, which can be from 4 kilometers to 25, and we run our own method for interpolations, and we create half-kilometer resolutions grids from which we retrieve all information that is needed for further processing. As for energy nowcasting, it is what we have implemented the last year. So within the day, we correct our forecasts based on real data from photovoltaic and wind power plants. And by means of this, we are able to reduce the errors depending on hours ahead. So it's like 5%. And after 4 or 5 hours, there is already no effect in this. But generally, if it is taken all together, so the reduction of error is up to 45% in some cases. What is needed in case of predictions of wind power energy is also, I think, it's a big problem in Czech Republic, because in certain conditions, it means total stop of generation of wind power. For this, we have our model, which is based on WRF. Well, and electricity consumption, it is another product that we create. Here it is very interesting because you need to combine both weather factors that come from numerical weather predictions models, but also socioeconomic factors. It's dependent on day of the week, annual cycle. It has some special behavior in case of holidays and so on. On this plot, you can see how the consumption changes from year to year. So in winter, there is higher energy consumption, in summer lower. It depends also on hour of the day. It has daily cycle, and it's also dependent of day of the week. So different lines show different days of the week. And then there are weather factors. What we use is dependence on air temperature and cloudiness. So on this left bottom plot, we show dependence on temperature, here on cloudiness. And here is only example when there is sunny on a cloudy day, what is impact on consumption during the day. On the last slide, we devote also to hydropower plant forecast. Here we used 4-day ahead forecast, which is based on precipitation data coming from numerical weather prediction models. But then we use also our own soil moisture model and also own hydrological model for river discharges. And the calibration is again based on historical data, but also we devote to nowcasting. So that's all from me, and the rest, other details, you can find on the poster. So thank you for your attention.
Thank you very much, Peter, for your presentation. That was very interesting. Do we have any questions for Peter, either in the chat or if you want to raise your hand? Can't immediately see any questions. One question from me then, while others are thinking. You said that in order to sort of have everything on the same spatial resolution, then you're kind of going from possibly 25-kilometer resolution down to 500-meter resolution. That's obviously quite a big jump. Can you say a little bit more about the techniques that are used there and how that adjustment is done? Are you using additional topography data or surface roughness or things like that?
Yeah, you are right. It's not so easy. And what we do is you have model orography, and then you have real terrain. So what we do is conversion data between the original model topography to the real one. We use simple linear regression, but the regression is calculated for each time step of the model. And we have experiences for this from, for instance, also because we devote also to drought monitoring and forecasting. So we have here, well, the data can be found on web pages. Yeah, so that's why we also use it here, because if you have everything in this half-kilometer resolution, so then it's very easy to retrieve many products from it. I mean, the same, sure. You just look through all the models and you can create a combination of the models I have spoken about, but also to estimate uncertainty, which comes from different models, and it's very useful.
Mm-hmm. Okay, brilliant, thank you. Any other questions for Peter? I can't see any other hands. Okay, thank you very much, Peter, for your presentation, and Frank as well. So yes, we only had the 2 presentations in this session, but as was said earlier, this is kind of a bit of a new topic for this workshop. So we do have some opportunity for some discussion now if people want to offer some more general thoughts on this. Obviously, a lot of the focus on, to some extent, on this and previous data management workshops have focused on the use of in situ observations and perhaps to some extent remote sensed observations, satellite data, for example. There have been several presentations in this workshop about the use of reanalyses. There was the one earlier in the session on data sets, and then there was the presentation earlier today about use of reanalyses for homogenization, and now the use of both reanalyses and NWP models for providing services. So it'd be interesting if anybody else had any experience of using reanalysis data or NWP data for climate analyses or providing services, not necessarily for the energy industry, but maybe in other applications. So so I don't know if anybody has any comments or thoughts on that.
Maybe I would have a comment.
Yeah, sure.
We use reanalysis data, especially ERA 5 land for drought monitoring. And what we have found, and I would like to ask others if they have also such experiences, is that similar to climate models, which have wet bias, it means that, for instance, in Czech Republic, they show 100 millimeters more precipitation, and then they are colder. But the problem is the wet bias, and it is something what we have found also in this reanalysis of ERA 5. And then it means some problems during the drought monitoring that we run.
At least I can say for our side that we did not specifically look at that problem, so I don't have an opinion on that.
And may I ask you, Frank, if I understood it well, so Cosmo reanalysis, it is available only till the end of 2019. It's not available up to now.
Yeah, because the idea of the reanalysis is that everything should be as consistent as possible. So we used ERA interim boundary conditions, and they stopped the production of that. So the ECMWF shifted towards ERA 5. And we are going to set up a new regional reanalysis that will consistently be produced with ERA 5 boundary conditions and covering also 30 years. But this is currently in preparation, so it's not yet available. But the idea is to really have a near real-time updates of these data sets. But for regional product, we depend on other producers of the global data sets, and therefore we had to stop in that year.
Okay, because we would be very interested in using your Cosmo analysis in our studies. So when it is available, we will be.
Yeah, we will somehow announce it, probably on our Twitter channel or at the next workshop. Wow, but that would be in 2 years. No, we hope that it will be available in the next year. But we have to look at the quality before we release it. Of course, we hope to improve something compared to the previous version.
And can I ask you, when you compare Cosmo analysis to ERA 5, so you get the same results, I mean, with respect to precipitation and temperature? I mean, especially biases. It is what I'm interested in.
But what do you mean by the same results? What I have shown in my presentation is that we can show that for wind speed, there is an improvement, an added value compared to the global reanalysis. And we have also looked at other parameters. So in a lot of cases, we can demonstrate an added value. You can never be sure where it really comes from. It's just the improved topography, the more regional details, or is it really because of the data assimilation? But for a range of parameters, there is an improvement, but that's not necessarily always the case. So if you look in this review paper, I just have put the link into the chat. So there we discussed everything we know, and we are also referring to other studies. So some people looked at precipitation. And for example, for precipitation, there is also an improvement compared to the global ones. But to some extent, that's just because of the higher resolution. You can capture better the extreme events, for example.
Okay, thank you. We will check the paper. Thank you.
Okay, brilliant. Any other comments on use of reanalysis or biases in such data sets? One other thought from myself, I mean, many years ago, I was a little bit more involved in doing consultancy work myself from within the Met Office, but and we used software, something called WASP, Wind Analysis and Application Program, which I think was produced as part of the European Wind Atlas that was published probably in the early 1990s, I think. I think the software itself may still exist, and that was a kind of a boundary layer model for taking in situ surface wind speed data, you know, from a Met site for which we had 10 years of observations or however long, and you could kind of use that along with topographic data to and land use data to kind of create an estimate of the climatology at a target site, such as the location of a wind farm. Do such tools still exist? Are they still in use? Have they ever been compared with reanalysis or other such tools? I don't know if anybody has any thoughts on that.
Well, of course, we did not do any possible comparison that you could think of, but there has been this activity, the so-called NEWA, New European Wind Atlas. So I think it has been released last year or so, could be based on similar approaches that you just mentioned. Well, the main point that I see here as a difference is that those people who are using those tools externally, they don't have access to all the observational databases. So the idea in the reanalysis is that the same as in NWP, you try to consider all the meteorological observations and that you can get access to really how do you call it, to really estimate the real state of the atmosphere as good as possible. And well, that might not be too relevant if you just look at the long-term averages of wind speed, but when you also want to use the data, let's say, to look at detailed weather patterns at specific extreme events, you can think of a lot of studies that you can do with a reanalysis data set. So I would think that the main advantage is that you really are close to the real behavior of the weather systems, also at a specific time and location. And we have other activities where we look at extreme events. So how good can we simulate a specific storm event at the coast, for example? And there we can demonstrate a clear advantage that you get as a result of your data assimilation. And that would probably the major difference between the two approaches. But this is just some speculation of myself. So we are interested in these comparisons, but we could not do everything that you might want to see.
Of course. Yeah. Okay. Thank you. Any other comments? So one other sort of thought that I was having prior to this session on a completely different direction, as it were, sort of thinking about routine climate monitoring and how that might relate to services that are provided for the energy sector or other sectors. Now with other things like temperature and precipitation, then there are a whole lot of recognized indices, the ETC CDI indices, for example, which are all temperature and precipitation based indices. I was just wondering whether there's any merit in coming up with some indices that are more related to wind, or in particular wind energy, or radiation, or sunshine duration, or something like that, that perhaps different Met services could agree on and derive from their data, so that collectively we can perhaps monitor changes in such things. I don't know whether that that is a sensible idea, or if anybody has any thoughts on that.
Well, I could say
ahead,
something again, but I would also leave space for others. Well, at least I can comment that there is a big interest in monitoring of wind speed in Germany, and we have been careful on that based on our station data, because I think we are all aware that the station-based wind measurements have more homogeneity problem than other parameters. So at least that's what we assume for a German time series. So we did not provide an operational monitoring product based on the station information, but we received a lot of requests on that. So there are indeed a lot of governments, active government agencies active in the energy sector, for example. They would at least receive some statistics and include that in their annual reporting and monitoring and so on. So we are currently in discussion how we do that. And for that, they would be really interested in seeing near real-time updates of the reanalysis, for example. And then they would like to have some aggregated information on that. And as we all know, the mean wind speed is not really relevant for the energy application, because you have this dependency on the nonlinear dependency on the wind speed.
Yes. So you could imagine some other parameter that was maybe, I don't know, number of hours exceeding some threshold, for example, or
So there is something called like the capacity factor used in the energy sector. So there's this how much % of the real installed capacity you could gain at the end. So
okay, yeah. So maybe we can learn from the sorts of things that they are interested in. Yeah. Okay. Thanos, I see you have your hand up.
Yeah, I want that the common practice until now is the reliable distribution and publish.
Oh, I can't hear you at the moment. Oh.
Can you hear me now?
Go ahead. Yep.
Yeah, the common practice until now is to scale and shape parameters.
Yeah. Okay, I caught some of that. I think your audio is breaking up again, but you were talking about the Weibull distribution and shape parameters. I think you said, yeah.
Scale parameters, yes. Well, this if applied in several time windows. It's quite rough. It's not very detailed.
Okay. I didn't catch all of that. I'm afraid. Sorry, but thank you. Okay. Yeah, I think. Do we have any other comments on this, or even comments on whether you think this would be a useful session to expand in a future workshop? Frank?
Well, I mean, I presented one slide that was based on a comparison of results with other meteorological services. It was actually based on a 4 years European project. It was called UERA, and for example, also UK Met Office was involved. And it was really helpful for us and also for our arguments against other agencies. Well, what is really the quality of the data set? So the intercomparison among agencies helps us to show that we are working on the state of science. And therefore such cooperation in Europe would be helpful for us, but I'm not sure. So at that time, it was actually 4 major meteorological services that were working on reanalysis. So it was UK, Sweden, Météo France was involved, and also Germany. But I think UK is not active on that anymore. But my general answer would be, for us, it would be of interest to have such intercomparisons at the continental scale with others who are active in the sector. But it needs some resources also.
As always, yeah. Yeah, indeed. Okay, good. Well, oh, Gerard, I see you have your hand up. Yeah, go ahead.
Relating to your question, so I think the idea of having something about energy meteorology in this workshop, that is I think a very good idea. So during Frank's talk, I already pushed some information to some of the PhD students we have at the university here around the corner, who are working on this particular field. They are not meteorologists, but they are from physical geography and things like that. And the role the KNMI takes is in servicing these people with information and data. And I think much like what Frank is doing and others probably. Would it be an idea to try to attract some attention from these people who are much more on the energy, active in the more energy field rather than the meteorology field, to have a perspective from their side on how useful the reanalysis data actually are for their work? Would it be valuable?
I think that would be excellent. Yeah, to get the perspective from the users of these things, a bit like your question about whether the German government was found the products useful. So to find out, yeah, whether the people who are working with the data or using the final products, because sometimes they they have different terminology, they have different priorities, they have different expectations, I guess, of the data, and to understand that would be really good. And often we at these workshops, perhaps understandably, it's quite a lot of people from national Met services, and to get some perspective from other users of the things that data sets that we are creating would be, I think, very valuable.
So yeah, one of the questions suggestion. I always get from these people is that the time scale on which we are working, so we're producing data on, say, 6-hourly level or perhaps 3-hourly level, is often too coarse for them, as much of the impact models they are using in trying to balance the energy system is on much shorter time periods. And
okay, yeah.
So perhaps we would have a discussion how to bridge that gap, or perhaps we could add suggestions how to bridge the two worlds.
Yeah, definitely. Okay, that's good. Barbara.
If you would like to have this topic included in the next workshop, should it be restricted to energy, or would you like others as well to be involved?
You mean in the sense that it's just a session on reanalysis applications?
In a sense of the use of the data,
okay,
how it is used, time gaps, things like that. Would it only be for energy applications, like the session we had now, or would you need to have it enlarged to more users or stakeholders?
So if there are such applications, that would be of interest for me, at least. But as I said, we analyzed in this review paper how much applications do we see from different sectors, and we saw the majority of applications in the energy sector. So therefore, the audience could be, well, biased toward that sector, even if we open it to general applications.
I guess in a future workshop we could keep it fairly broad and invite you know, abstracts for anything where there is application of the data, and yeah, if it ends up being all the talks are to do with the energy sector, then that's fine. But perhaps we shouldn't necessarily restrict it to that. I think was it Peter was talking about drought monitoring as well, and so there are perhaps other areas that could be combined in a session like that in the future. Okay, brilliant. Well, I think we're approaching 1 o'clock in the UK. I guess 3 p.m. in Athens, is that right? And 2 p.m. in much of Central Europe. So which is meant to be the end of this session. So thank you very much to the speakers and to all of the comments and other contributions in the discussion. I think that's very useful. I'm sure discussion about future plans will be picked up in the, I think there's due to be a break now, Thanos, is that right? And there'll be some more discussion after that. So, yeah.
Thank you very much, Dan, for chairing this session. We'll have a 12-minute break, and we will resume for last open discussion, overall workshop. Thank you very much again.
Okay, thank you.
Thanks.
During the last meeting, there was the wish to have some discussion on the communication of revised climate information, especially based on the fact that the new climate normals are due now or have been calculated this year. And so we decided to include this into this data management workshop. So I invite everyone to participate actively in the discussion. Thanos will be very happy to give all of you the opportunity to speak your mind. So if you want to, if you can't unmute yourself, please just raise your hand and Thanos will do this for you. So to start, the new climate normals are out for at least some countries. Did you have any issue in communicating them, or did everything run smoothly for you? Is there anyone that already? Yes, Eric?
Yes, we have published some few normals for temperature and precipitation for Sweden yet, and we're working on other parameters. And I think the interest was very large in Sweden. It was a lot of people, the media and so on, asking, waiting for it, and then they also, the media asked to have the, how we say, the data, what we based our, we also produced maps over Sweden for the climate normal values, and they asked also to have the information to draw the maps. So we also have made that available on our webpage. So that I think we got a good response from the society in Sweden, and but we also have a lot of work to do yet. And one problem is to fill in the gaps. So that's why we only started with some few parameters yet, where we had available gridded data set to fill in the gaps. So that is a question to colleagues here. If you have the same problem, and if you had a suitable method or data to fill in the gaps to produce the normal values. Thank you.
Yes, Joseph.
Hi, Barbara. Hi, everyone. Can you hear me?
Yes.
Okay. Regarding Israel, we've published recently the climate normals only for precipitation. The temperature is on progress. And after publishing them, we've even managed to make a nice report that comparing actually 3 standard normal period, 1931 until 1960, 1961, 1919, and the recent one, 1991, 2020, and including maps, annual maps, and monthly, and monthly amount. And even with input over there, some trends regarding the number of precipitation days. And we gave some seminars and lectures about it, and it's really nice. Thank you.
Thanks. Did you also homogenize your data so that the old normals changed to what you have communicated before, or did you
No. Yeah, where we have kept the same technique, the same methodology. We've got our homogenized daily precipitation since 1950 until 2020. And by the way, regarding Mary comments about after you are calculating, after you homogenize your time series based on the monthly values, what about the daily indices? And she's right, it's a big problem. But after you have a daily homogenized daily indices, so you can calculate this indices quite easily and look for trends. But regarding communication, and maybe this is another aspect and not the scope of this session, but if we are looking or asking what was the highest value or the lowest value, if we're interested in the absolute values, should we take them from the homogenized database, or we should take them from our raw data that was that undergone quality control, of course? Or if you are interested in a specific heat wave or specific storm, should you use a homogenized database or using your raw data, which passed quality control? But maybe this is another topic. But regarding the averages, we didn't make a thorough homogenization about them. Of course, a well quality control procedure is done. Thank you.
Thank you. Gerhard?
Yeah, so regarding the climate normals, I think there are perhaps three things I would like to say. So one of the experiments we did with the previous climate normals was to team up with an atlas, so a publisher of atlases in the Netherlands, and they have a new series where they not only provide topographic information, but also information about more contextual things like climate, for instance, in the Netherlands. And they seemed to be interested in a climate atlas for the Netherlands. And so apart from the WMO publication we usually make, which is always a bit dull, we also provide this information through a climate atlas. So perhaps that's an interesting idea for other Met services. So relating to one of the comments made earlier, one of the problems we stumbled into with the climate normals is not so much the calculation of the climate normals, but reproducing the climate normals of the previous period. So it turns out that some of the software we used was perhaps not so robust for the changes in time. So we had quite some difficulties in getting well, the bit of the documentation we had in order and understand what was being done to make sure that the climate normals would be, of the previous climate period can be reproduced. So that was actually, that took most of the energy of producing these climate normals. So there was not so much a problem in gap filling as what Eric mentioned, but what we do see is that the breakpoints between two stations is now, of course, shifted in time a little bit. So that produced some difficulties in getting things completely right. So relating to Joseph's comments, what we do when communicating, say, the number of heat waves where actual daily values are used, we use the homogenized data for that, and so we do not use the raw data for that. And that did produce some problems, of course, in the press, because it turns out that some very hot years in the past were then robbed of some of the heat waves which were observed then. But we think that using the homogenized data also in these climate services is the way to go. Thank you.
May I say something?
Yeah, sure.
Yeah. Thank you, Gerald. But we all know that when you are homogenize your time series, you can choose whatever to correct your time series from the recent period and backwards. You can do it actually the opposite. You can correct your time series from backwards until today, but every new value that you will get, you need to correct it. So if we are looking on an absolute value, it can be a bit problematic. For instance, if I will ask you what was the lowest temperature that ever measured in one of your station, which record you will, on which record will you report? On the homogenized one that you gave him a correction factor, or on the raw data that passed quality control? This is the point.
Yeah, that's of course a very valid point, and that's exactly the difficulty in this. And I think Eric also illustrated that once you start homogenizing, then when you do a second run of your homogenization, you might get different results again.
Yep.
So that is really a tricky discussion. That's true. But when people ask for the highest temperature or the lowest temperature, and we have a homogenized value available, then we provide that particular value.
Oh, interesting. Thank you for that.
Yes, Jose?
In this respect, I would vote for providing the actual record, because if the question is what was the maximum temperature ever recorded at that station, if it passed quality control, I would refer to the raw, not to the homogenized. For other questions, then yes, it's better to use the homogenized series. And connecting with climate normals, we have calculated, for example, for extreme temperatures and precipitation at the Madley scale for monitoring purposes. But another question is to answer to WMO call of providing the normals for several variables and providing them in a very particular format in CSV. This is work that is beginning in EUMET, and I contributed with a script for calculating all these normals and formatting them in the requested CSV files. But it works only if you provide homogenized and all missing data filled in at the daily scale of the variables. Just this. His name is Kleino tool, if you are interested. Thank you.
I think it's Clino. Clino, it's the name.
Clino tool, yes, I pronounce some word in English.
Yeah. We are now implementing it, and we are calculating it for temperature and precipitation with all the percentiles, the averages, median, and so on. And there is a specific format, but yes, this is actually what we are doing these days.
Okay, thank you for the feedback.
So this is downloadable, the software, this Clino software?
Yes.
It's an R package. It's an R script.
Okay.
It has examples and you can reproduce them very easily.
Okay. Mary?
Yeah, I was just going to ask, could you put the name of that software in the chat, please? It's breaking up a bit for me, so I'm only getting bits of the conversation. Sorry.
Yeah.
Okay, yeah, I will put the link to it.
Thank you.
It's linked in WMO pages where the call for the climate normals calculation is made, but I will put in the chat.
Okay, thank you. Is there anyone having similar issues as Eric? Oh, yes, Eric, would you like to add?
Yes, thank you. Yeah, it was discussed a little bit before about recalculation of the older climate normal periods, and because now we have a lot of more station data available digitized compared to when the normal period 1961 to 1990 was calculated the first time. So we recalculate it again now with our new method with more data available. for it. So it did not change so much, but we think it's much more robust now. So it's we think the quality has improved a lot, although it's not so much different in the actual numbers. So yeah, thanks.
So you did the maps and the graphics, so calculated a grid with the old data for the older period.
We use the data from our database, but in the database we have now much more data than we had for 30 years ago for this 61 to 90 period. So to say.
Okay. Thanks. Yes, then.
Thank you. So regarding several questions, so for the climate normals for the UK, we are still working on those at the moment, aiming to have them finished by the end of November, so we haven't published anything yet. The idea of a published atlas is an interesting one. We certainly haven't considered that previously, but
you are not too loud. Could you please speak up a little bit?
That's because my microphone was
Thanks.
at the top. Sorry. Thank you. Yeah, I was just saying that. So for the UK, we only plan. Well, we have not completed the work yet, so we haven't published anything yet. The end of November is our sort of target for trying to get the work complete. We have been liaising with MET-ERN. Obviously, we have a common boundary with Ireland, and so sharing of data and trying to coordinate perhaps the release of our data is our aim. I need to catch up with Mary and her colleagues regarding progress regarding that. So I was just saying that, yeah, the idea of a published atlas, that's an interesting one that we haven't done previously, or probably not for 30 or 40 years when published books were more common. But yeah, recent work on climate normals has only been really released on our website. Regarding filling in gaps in data, then the method that we use, we continue to use a method that a colleague developed many years ago, I think when the 61 to 90 normals were first done. And that basically takes the monthly station data and looks for well-correlated neighboring stations with overlapping data with the target station. And then creates a regression relationship between the neighbor and the target, and then uses the value at the neighboring station for the missing month to make an estimate for the target station. And then it does that using up to 6 neighbors, and then creates a weighted average of those different estimates for the to create the final value for filling in the gap. So we have our own software for that, and I've recently been working on migrating that. It was Fortran code last time round, and is now been migrated to Python. Regarding the question about quoting of extremes, so we are a relatively small team, and in fact we don't have this issue because we don't actually do much in the way of homogenization. So I'm obviously well aware that that would be a good thing to do, and many other Met services have invested a lot of time on doing homogenization, but we have not been able to incorporate that in this work. So the normals that we will produce will be based on unhomogenized data, and certainly when we're quoting extreme values for individual events for the press or the media, that sort of thing, then it would be based on the raw data that has successfully passed through quality control. I really don't know what the right answer would be if we had homogenized our data and had that choice about whether we quote the homogenized value or the raw one. I would probably agree. I think it was Jose saying about perhaps going with the raw value. I think that would be my inclination. In a sense, the benefits of homogenization are more in the way of looking at, I would say, trends and getting a better estimate of changes, consistent time series and so forth. Whereas for an individual event, as you said,
Is it my system where I can't hear it then anymore, or is it for all of you?
With Dan's connection, I think.
You could be adjusting vice versa, so there is no observed value when you're quoting about. I think that's it for now. Thanks.
Thanks, Dan. What all of you? Yeah.
Perhaps Dan should repeat his last sentences because they were lost. There was a problem with his connection.
Dan?
Yeah, I was trying to think what my last sentence was.
The last part.
Sorry, I've lost my.
It was about the individual raw data, using it for records.
Oh,
yes.
All that thank you. Yeah. Oh, okay. Thank you, Mary. Yeah, no, I was just saying that in my opinion, I think that for individual records, we would definitely quote the raw value rather than the homogenized series, because I see the benefit of homogenization really is getting a more accurate estimate of the trends and so forth, rather than trying to correct an individual value for an event. At least that's my feeling, and I think the point that was made earlier, that you could make the correction either to the historical part of the series to be consistent with the recent data or vice versa, means that it's just it's too difficult, I think, to then communicate that in a clear way if you're talking about individual events. That therefore you would stick to the raw data, but that would be my feeling anyway. Okay, thanks.
Questions to those not doing the climate normals or homogenization. What would you expect to get? Which data would you expect or wish to have included in a data set? If you want some analysis for over a longer time period, would you expect the creator of the data set to use the homogenized data or the original data? Which one would you prefer?
If I may.
Yeah, sure.
Question on this topic by colleague. The name is Sonia. I don't know if I pronounce. Have the possibility to ask your question.
Yes. I didn't really hear you what you said. Was there a question or?
There's a question on the chat.
I can't see it. Can you read it, please? Oh, here it is.
Yeah. Getting now new climate normals from homogenized data.
Yes.
But should do the small services as the one in Estonia are not able to create homogenized data sets?
I think WMO is saying that if you can't do that, it's not necessary to do it, and you can just use the data you have. There have been 2 workshops. Thanks. See? There have been 2 workshops of the WMO on the new climate data sets. I'm not sure if you can rehear them. have they been recorded? Jose, do you know that?
No, I'm not sure, but I don't know. Maybe not.
Okay.
I think you can get the notes from them, but not recordings.
Okay, if there are some notes that might help. So whom would Rena best contact for that?
Would it be Per Heckler?
I think so, maybe. Rena, do you know Per Heckler and his contacts, or should we put it in the chat? Jose, you want to add something?
Just to tell that these consultations that were made as teleconferences with the different regional associations were just to explain and to solve questions of our members. But anyway, there is a publication about the WMO, how to calculate the normals, and there are lots of details, and there's stated that it's preferred if they are homogenized, but it's not necessarily the case.
Could you put the link to this document in the chat, please?
I will try, yes.
Thank you. Dan?
Just quickly to say that, you know, as I said earlier, at the Met Office, we don't have the resources at the moment to homogenize all of our data. So we are going to be producing climate normals without homogenization, and we accept that that's not perfect or not ideal, but I think it's better to produce some climate normals rather than none, and document the method and the limitations accordingly. So so even if WMO recommend homogenization, I think it's still we should all try and produce what we can, I think, with the resources that we have.
Yes.
Yeah, the link is in this same link that I put for the Cleaner tool. The last reference in this web page links to this, how is it called? WMO guidelines on the calculation of climate normals.
Okay, thank you. Is there any other issue? Yeah, Petra?
I have one comment regarding unhomogenization of data. Yesterday, I have shown during my presentation an example of wind speed and precipitation that without homogenization, when we have newly automatized measurements, so it influences trends very much, and it means also level. The question is if you want to correct to the past or to the future, but anyway, unhomogeneous data, they have quite different trends. And I think today I noticed it was also of that temperature. It was shown in some of the presentation. It means in any of the elements, we have automatization, which influenced the level in precipitation to lower values, for instance, and wind speed to higher. But anyway, trends. So we should homogenize data, I mean.
Do all of you trust the homogenized data?
Yeah, that's the question.
This is a big question because there are several techniques of the adjustment, not just for breakpoint detection. If I'm choosing to use a Vincent method or quantal mapping method or other methods that were mentioned during this workshop, you will get different numbers on a daily basis. And it's really depend on the way that you are doing or applying your correction factors. And I think that Dan summarized it very clearly. and I fully agree with him. The homogenized database was mainly made for looking for climate trends, for a good assessment of long-term trends. But if I'm interested for a specific event, I think that we should go to the raw data. Because if my station was in the city and then it was moved to 2 kilometers to the north or to the west, it doesn't matter. Yes, for sure, there can be an abrupt change in our data. But if I'm looking for the minimum temperature that was measured in this area, I think that I will use the raw data because it passed quality control. The first segment is homogenized, and the second segment after the breakpoint is also homogenized, just for the example. So I think that we should use the raw data when looking on extremes. And if I would like to measure the magnitude of a heat wave, for instance, or a specific storm, how many rainfall was measured during this storm, I think we should go back to the raw data. But when talking on trends, for sure, the homogenized database is the best. Thank you.
Thanks. Peter?
Yes, so Yitzhak provoked to add something. So yes, the homogenization method give different results, and it would be good to have standard ways of testing. So no, not each case something improvised tests, because they also give very different results. But on the other side, it is a general experience that homogenized data, generally, not always, more accurate, closer to the reality in many cases. It has several problems. I don't want, it is not the place to speak about all aspects, but generally the homogenized data are closer to the truth. There are some exceptions, and we should mention special problems. In any case, when we select between a raw data or a homogenized data, or how it is fit to the end or to the starting point of the time series, each time the best selection is, but according to our knowledge, is closer to the truth. It is not, we should not say here to have a general rule. Anyhow, thank you. I have learned a lot in these 3 days, and I am a bit surprised that relatively few number of participants, because in with remote access, it would be easy. In the world, a lot of climatologists use climate data, and so interesting information does not reach the users of climate data, the climatologists. Thank you.
Thanks, Peter. Mary?
Hi, it's just a comment about homogenization. I think even inside Met offices, it's people don't exactly, the other meteorologists don't exactly understand homogenization, that we haven't communicated it to them. So when I'm explaining to people that I'm looking at the trend in data rather than the actual, an absolute record, they don't really understand. They haven't got that message yet, you know, and it's quite hard to communicate that, I think, at times to other people, what we're actually doing with homogenizing the data, or why we're doing it, what the use of it is, you know, because we have a thing now, obviously records are being broken, and there's certain steps we have to check, you know, the calibration of the instrument, etc. But immediately they say, oh, go homogenize it. You know, and that's their answer to fixing the records. They don't understand more that we're looking at the trends.
Yeah.
Yeah, I agree. It's out of question that homogenization is improving the evaluation of trends. But I have doubts, even if now there is an increased interest in the homogenization of daily data, to what extent the homogenized series in the daily data improve some parameters like related to extreme values. For example, how would be the return periods of some variable in the raw series or compared to the homogenized? It's something that I have not checked, and I don't know if anyone else has tests. On the other hand, as we are arriving more or less to the end of the meeting, I would like to explain why I put my private email there before in one message. It's because 2 days ago I reached 50 years of continuous service to the Spanish Met Agency, and this will be my last week of active service, active work in here. So I will be retired on Monday. But anyway, I plan to remain active in homogenization matters, possibly also available to WMO for data management working if I'm required to. Thank you.
Thanks, Jesse.
Good
Thanks
luck,
for all
Jesse.
the work you did for us or for the homogenization community. Hope you will stay there. If you want to compare two different single events, would you do that on homogeneous data or on original data? Did any one of you do that? Doesn't seem like it. Oh, there are some messages. Is there any other issue you have with change data sets that you do need or would need to communicate? Yeah, Gerard?
Yeah, well, I'm a bit hesitant now to say anything, but given the discussion we've had a few minutes ago, I was wondering, are the participants not worried that when they use homogenized data for their trend values and non-homogenized data for other climate services they provide, that they are actually communicating that there are two kinds of truths? And doesn't that give some confusion in society? So what we were worried about is that when people wanted to recalculate, say, the number of heat waves or so, using either the homogenized or the non-homogenized records, which involved, of course, the extremes in temperature, then they would come up with two different answers. And so that was one of the arguments why we opted for using homogenized data more consistently throughout our climate services. I agree, though, that there are many issues which are difficult with the homogenized series. So I can't counter all of the arguments which have been produced by Joseph, for instance, but we are struggling a bit with this.
Are there any comments, further opinions to that? Joseph, did you have any issues with communicating a trend from one data set and values from another one?
Sorry, I didn't hear you. I didn't hear you.
Sorry. Did you have any issues with communicating the trend of the homogenized data set and the extremes of another one, of the unhomogenized one? Did no one noticed that so far? Or?
Actually, no. I think this is really a big problem, like Gerard said. And we have already published our homogenized daily data for precipitation and temperature, and it is not combined with the raw one. The original data, the raw data, after well quality control, is as well published. It's free, you can download it for free. It's in open data. But the homogenized database is published in another place with a very well documented README paper that I want to believe that if you wish to use this homogenized database, first you should read this documented that go with this data. And over there, I have wrote in bold letters, what does it mean when you are using homogenized database? And I emphasize over there that this is not the database for analyzing a specific day or a specific storm or heat wave or any other extremes. It is good for looking on trends on extremes. For instance, if I will track the highest temperature, the one value, the highest value that was in my database, I can see the trends for 50, 70 years, and I can report on this trend, and it is okay because it was homogenized. But if someone will ask me what was the highest temperature in this region, I will go back to the raw data, the well quality controlled raw data, and I will give the number from there. This is my point. Yes, but it's a big problem to communicate it, because homogenized database, it sounds like a gold standard that everyone would like to have it. And now when you have homogenized and there are no missing data and all your data sets is very in a high quality, okay, now you can run whatever you want. But if you are interested in an absolute value and in specific days and dates, it is really important to bear this issue in mind. Otherwise, you may get to wrong conclusion, because as we all agreed about it, at least we agree about it, that we can correct our time series in different way, and we can decide it if to correct them from the recent to the back and from the past to the recent, and it will change the absolute value for sure. For sure.
Yeah.
Yeah.
Is it possible to have access to this document you wrote?
Yes, but it's only in Hebrew. I didn't translate it to English. Sorry. But I think it will be a good point maybe to discuss it more during our homogenization colloquium, and maybe it will be interesting to open it, to reopen it again with the homogenizer.
Yeah.
You can always use the Google Translator.
I'm afraid about it.
Then?
Yeah, thanks. Two points. One, going back to Gerard's comment about kind of two types of truth by having one homogenized data set and one unhomogenized data set. I guess if you are wanting to make a comment about a recent event, to say this recent event has now set a new record, then that implies, excuse me, implies that the homogenization, if you are going to homogenize your data, must have taken place to adjust the old part of the record to the new part, so that new observations that are being made today or tomorrow can be compared with that series. So I guess that implies you would have to do the homogenization that way round. So that was one thought. The other thought was to do with, so when we homogenize data, there are different types of change. So obviously, if you are having a change in the equipment, then you could clearly argue that you do need to make an adjustment. So if you're making, if you're taking an observation today, using one type of equipment and trying to compare that with an observation made 100 years ago with different equipment, then you would need to make some sort of adjustment in order to be able to compare those two values. But if you are talking about something different, like a change in the location of a station, perhaps from an airfield site to somewhere else in the same vicinity, then that seems like a different thing, because that is, those observations are a true representation of those locations. You know, the airfield site may be a little bit cooler or warmer or whatever than a site 1 kilometer away on the other side of the town. So those are accurate measurements of those locations. Now, I understand if you're interested in trends, then you need to allow for that. But if you are talking about events, then you know, that is the temperature that occurred at those specific locations. So you could argue that to compare events, you need to homogenize for certain types of change, but not others. But that's a whole different complicating factor. But anyway, that's my thoughts.
Thanks. Mary?
Hi, I was thinking the same thing as Dan about location does make a difference. So you reported for the location, but the problem with the equipment change is it is corrected for the present equipment, but not every station has got the new equipment. So it may be actually just a case where another station where it's still, for example, had a mercury thermometer, it will now have the record, but it might be because it hasn't had that change, you know, because there was no change in the actual equipment. So yes, equipment does make a change, but whether it solves the problem, I'm not sure. I don't really think it does. And for example, say with, I think I showed it in our sunshine duration, it's because we corrected back with a station, but it gave it roughly 70 hours less than a station nearby. But that was because the exposure has got worse at the station rather than the equipment has changed. You know, so the record, you're changing it back to get it to make it less, but it's not actually true. It was more due to the exposure, and it was only we got the metadata that we discovered this. So I think there are still lots of problems with it, you know, with equipment. I think it's something that we really need to get together about and maybe come up with what we actually agree about, you know, because I think it's very dangerous, as Jared says, where you've got two truths, you know, that it just doesn't make sense to the public, you know.
Thanks, Mary. Petra?
Maybe I would like to express my fear following the previous two comments. In Czech Republic, when we changed to automatization in the whole area, in case of, for instance, precipitation or almost all the stations, and the automated measurements are completely different from the past. So I think this is really a problem. Yeah, understand. Because we know that we measure something completely different from the past with the new equipments.
So parallel measurement may help in this case. Parallel measurement.
Unfortunately, we do not have it.
Yeah, so it's a problem.
But I did not want to end with some pessimistic ideas, but this is really what I'm afraid in these new climate normals that we have created in the Czech Republic.
I think we are all dealing the same problems.
We are.
Yep.
Is there any further comment? If not, I would like to conclude the workshop. Thanks to all the participants and to all the speakers for the nice presentation. We are planning to have another one in 2 years from now, as it will be in the same year as the traditional homogenization and interpolation event in Hungary. We are at the time exploring to combine the events. So to make it more easy for you to get to all the interesting events that are taking place. I hope all of you benefited in some way or another from this conference. And I would like to thank also Thanos for all his commitment and all the time and efforts he put into this workshop, and his team as well, and to all the scientific committee members that helped us as well. Thanks for that. Thanos, would you like to add something?
Barbara, I hope that you can hear me without interruptions. I would like to thank you and the EUMETNET for trusting the organization of this workshop to the Laboratory of Atmospheric Physics. It was a pleasure to host this event. It's a pity that you couldn't be here, but I hope that we'll have the possibility to host you in Patras. I would like to end with big thanks to Jose Guijaro for his assistance and the contributions to the homogenization community. Very much. Thank you all.
Thanks.
Thank you very much. Bye-bye.
Thank you.
Thank you. Bye.
Bye.
Good luck, Jose.
Bye.
Good luck.
Thank you.
Good luck,
Thank
Jose.
you. Thank you.
Bye-bye.
Bye-bye. Good luck,
Thank you.
Jose.
Bye.
Bye.
You. Bye.